have maybe 2 minutes to finish, and then we allow some time for the questions. So our first speaker is online, Orlando Tomazelli, and he will talk about implementation of O2 photolysis for Wacom 6. So I think we can pull it up.
Tell me if I can start.
We can hear you, so please go ahead. I think you need to share your slides.
I'm Isla Simpson. I'm
yes,
co-chair of
I will share.
Who is the other co-chair, and then Sarah Larson unfortunately couldn't make it in person to the meeting.
Okay, can you see my presentation?
Clara Desser.
Good, so go ahead.
Good. Okay, I will talk about the photolysis of molecular oxygen in the ultraviolet range, especially in the Schumann-Runge bands, and how it's implemented in the TUV.44 and Wacom 6. I will describe the Schumann-Runge system and Herzberg continuum. I will compare the parameterized versus line-by-line computation of the oxygen cross-sections. I will introduce in a new parameterization the correlated K coefficients of the cross-section of O2 in the TUV 5.4 and Wacom 6. And finally, I will discuss the effects of changes in the O2 absorptions on other molecules in the 0-140 kilometer range. At first, this figure shows us the Schumann-Runge system and the Herzberg continuum. In red, the Schumann-Runge continuum. In black, the Schumann-Runge band that are highly resolved predissociative lines between different electronic levels, and in blue, the Herzberg continuum. Note that both continua underline the bands. We can observe too in this figure in cyan line the parametrization of Cooper-Murtagh, that is the default parametrization in TUV and in Wacom. What is the importance of this? We can observe different products of the photodissociation of the oxygen depending the component of the Schumann-Runge system. The Schumann-Runge continuum products are oxygen singlet D and one oxygen triplet P, and for the Schumann-Runge bands and Herzberg continuum, we obtain two oxygen triplet P. And we know that these products are relevant in a chemical reaction of other molecules. The Cooper and Murtagh parametrization, the default and the unique parametrization in Wacom and TUV, is based on a line-by-line computation. It's divide the Schumann-Runge bands in range in 17 bins. It calculates an effective cross-sections, and depending the slant path for each level from the top of the atmosphere. So the cross-section decreases as radiation descends through the atmosphere. Here we can see the line-by-line computation of these bands at 200 Kelvin, and how the parametrization show two different lines for this the same temperature but a different altitude. In orange we can see the cross-section effective at 102 kilometers, and in pink the effective cross-section at 79 kilometers. The truth of this, or the best representation, is the line-by-line computations The Schumann Rundh band has something like 11,000 lines, but it's in theory we can implement this LBL calculation, but it's impossible to implement in a global model like Wacom because it's really computationally expensive. So we developed a new parametrization based in the correlated K coefficient using our line-by-line computation as input. These cross-sections are local, don't depend the slant path, and have no temperature limitations. We can observe in this figure green points that correspond to the Gauss points of the correlated parametrizations. This parametrization take the same 17 beams that use Cooper and Murta and calculate, in this case, 4 Gauss points for each interval and give to them a weight. We need to take account that the radiative transfer must be calculated n Gauss times. We can develop this parametrization for 4, 8, or 12 Gauss points, incrementing the time of computation. We implement in TUV the line-by-line computation and the correlated K computation and obtain a really good agreement between line-by-line and correlated K computation. We can see this in the red line. It shows the difference in the top axis. And we also implement the correlated K parametrization in Wacom, and we can observe these vertical profiles. We know that Wacom divide the J values of oxygen in JO2A and B, depend the products of the reaction, and we know that in Wacom, still persisting a typo in the Cooper and Murta range parametrization. We need to correct the first value of the intervals. So the difference we can see in this J value and the J values A is because we are amplifying the Schumann-Rundh continuous range. The difference in the other vertical profiles are causes of the correlated K coefficient and the range correction. We need to take account that Wacom and TUV have different vertical profiles of concentrations. So we can see difference about 100 kilometers. Sorry. In Tomaselli et al. 2025, we observed the changing the cross-section of the in this figure. That depends of how much the cross-section of the other species overlap with the Schumann-Rundh bands. Sorry. One of these species is CFC 114, and we can observe a really good agreement with the results in TUV and in Wacom. The positive of implement this new parametrization in Wacom is that we can observe not only influence of the cross-section of the oxygen in the photolysis of other species, but we can see also differences in the concentration of other species, like we see in these figures. We can see OH at the left and ozone in the right, including the correlated K decreases OH formation and therefore reduce ozone loss in the upper stratosphere and lower mesosphere. So we can conclude that the new TUV correlated K method model results in an excellent agreement with the TUV line by line. We implemented TUV vessel correlated K parameterization in CESM2 WACAM 6. Changes in JO2 affects the J values of significant numbers of species overlapping the Schumann room system, or that depends of the products of this photolysis. Including correlated K parameterization in WACAM 6 increase the computational times, but just 5%. Our future work is implement the correlated K method into the TUVX and inline system TUVX. Thank you.
Questions, if anyone?
Oh, just thank you very much. Great talk. We're just gonna follow up as you said there was still a typo in the model code with you. Maybe we can find out where it is.
Just this typo is in the original Cooper-Murtagh paper. In TUV, they resolved this in 2019, but in Wacom, it's still the typo. So when I was implementing this new parameterization, I find that this error, don't correct this error.
Thank you. This is June, Orlando. I will follow up with you with the typo, and we can talk about implement this new method in the inline TUV. I will send you an email.
Okay, thank you.
Okay, other questions? I just have one real quick. Do you know, does this impact, say, the temperatures at all in the thermosphere or mesosphere?
Sorry, I can't understand.
Does your changes,
can you repeat?
Does it impact the temperature at all? I guess not.
Sorry. If you can send me an email, I can ask your question better. But I can understand. Sorry.
Okay, I will send you a separate email. Any other questions?
Thank you.
So these are the trends in the gradient index.
If not, I thank you again, and we will move on to the next talk.
Thank you.
So next talk is given by Jen Guan, and it's on a limited long-term photolysis of stratospheric organic aerosols with implications for CESM modeling.
Thank you. Good morning, everyone. My name is Jian Guan from MIT, and I'm pretty happy to be here to present our recent work, limited long-term photolysis of stratospheric organic aerosols with implications for CESM modeling. First of all, I want to thank all my co-authors for their support and contributions to this work. And we know organic aerosol is an important component of the atmosphere, yet how much of it is destroyed by photolysis remain an open question. For example, Some models doesn't use any organic aerosol photolysis, while other models, including CESM, use a high photolysis rate. And of course, this photolysis intensity strongly shapes the organic aerosol chemistry. So it's quite important to understand what's going on for this photolysis. Here we are particularly interested in the stratospheric organic aerosol because in the stratosphere, organic aerosol is essentially important for climate and chemistry. These particles can scatter and absorb sunlight and provide surfaces for heterogeneous reactions that affect ozone. Here we want to ask two key questions. The first is, does stratospheric organic aerosol undergo significant photolysis or not? And second one is, if not, so what does that imply for CSM modeling? We know organic aerosol are widespread in the lower stratosphere, and there were plenty of campaign results observations shows that they are widespread in the lower stratosphere and with about 0.4 organic mass fractions up to 18 or 19 kilometers high. And also, we know the typical age of air in the stratosphere is in order of years, which means this organic aerosol will stay in the stratosphere for more than 1 year, making it very sensitive to photolysis. So since we know there are a lot of organic aerosol in the lower stratosphere, my first thought is that the photolysis should be very small or negligible because extensive. So we want to dig into it, and we look at the air campaign data from pumps measurements, which is a single particle analysis by laser mass spectrometry. And so we will look at the organic fractions from airborne observations. For the first panel, we look at the organic fractions within biomass burning air particles, and x-axis is ozone concentration. We can assume ozone concentration above 200 ppb is a stratosphere, and we can see in the stratosphere the organic fractions unchanged over the ozone concentration, and with these aerosols move upwards. And the right panel maybe shows even more clear, and we look at the organic fraction distributions within SABRE mission, and these three distributions are with different concentration of the N2O, which is a proxy of the age of air. So black line represents the aerosols are with the age of air of 0.5 years. Blue line is about 1.5 years old, and the red line is about 2.5 years old. Even though red distribution is 2 years older than black line, and we can see their organic fraction distribution keep unchanged, which proves that these organic aerosols are pretty stable chemically and physically. Besides airborne observation, and Australia wildfire actually provides a really great opportunity for the photolysis test, because after 2020 Australia wildfire, Paris CB inject a lot of wildfire smoke into the stratosphere, and it is dominated by organic aerosols with about 2% black carbon aerosols. And we firstly look at the AMPS satellite observation. It shows the extinction anomaly existed for over a year, consistent with the stable property of the organic aerosol. So we are wondering what if we put the same amount of wildfire aerosol into the model, so what happened? So we will back to a CSM model setup for a little bit. So CSM use a pretty high organic aerosol photolysis rate, and which is about 7-day lifetime against photolysis. And it actually follows these lab studies. These lab studies measure the fresh SOA photolysis for a short time. They measure it for about 30 minutes or 2 hours. So it's a short time photolysis. And we, in the model, in the CSM, we extrapolate these short-term photolysis into a whole organic aerosol lifetime. So since it's a pretty strong photolysis, so if we put the same amount of aerosol into the stratosphere, we find this organic aerosol disappeared within the first month and resulting no anomaly after the first month, so which is not consistent with the observations, the black line. So in the wildfire case, we also prove that this strong photolysis rate is not very correct, and CESM actually overestimates the organic aerosol photolysis in the stratosphere. So why does fresh aerosol, organic aerosol have photolysis while aged organic aerosol in the stratosphere doesn't? So recently, O'Brien and Crewell published a paper to answer the question, and they did a longer timescale experiment for organic aerosol photolysis, and they find actually fresh SOA photolyzed rapidly, but the rate falls down to near zero as aerosol ages. It is because photolysis destroys the light-absorbing chromophores, bleaching the SOA and shutting down the further photolysis. So since we already know the organic aerosol photolysis in the stratosphere is negligible, so how about we put it into the model and without any organic photolysis, and we can see in the middle panel, we in general reproduce observations in CESM2 karma, and in the right panel we can see the blue line, which is matched pretty well with the observations, again showing that we didn't observe any evidence for stratospheric organic aerosol photolysis. So if we know CSM actually overestimated the organic aerosol photolysis, so what happened for background organic aerosol, climatology organic aerosol? As expected, there are essentially any organic aerosol in the stratosphere, which is inconsistent with observations. And we compare the model results with campaign results, and we find in the stratosphere, model largely underestimated the organic aerosol abundance. So we are trying to fix this problem, and based on the theory, the fresh organic aerosol that have photolysis, but aged organic aerosol doesn't have. So how do we determine these aerosols are fresh or aged? So we use tropospheric air age. Tropospheric air age is 0 at the surface and increases as air circulates and ages within troposphere. So we can set up the certain air age threshold. So within this air age threshold, we think these the aerosols are fresh and they have photolysis. But when air age exceeds the certain threshold, we think these aerosols are aged. So we turn off the photolysis. So we try different parameters. We try and turn off the photolysis after 30 days, 50 days, and 70 days. And among these parameters, we find the blue line, which is with a turn off photolysis after 50 days, actually the best match with observations among these choices. So here is a quick summary. We actually asked 2 questions. First is, does stratospheric organic aerosol undergo significant photolysis? We answer these questions in 3 different perspectives. First, from the field observations, we find organic fractions in organic sulfate aerosols stay constant as particle age through the stratosphere, and which proof is pretty stable chemically. And for the wildfire case, we find organic aerosol from 2020 Australia wildfire persisted for over a year, consistent with negligible long-term photolysis case in the model. And for the background model simulations, we find strong photolysis would leave essentially no organic aerosol in the stratosphere, which is contrary to observations. So the answer is the stratospheric organic aerosol undergo negligible photolysis. So what's the implications for CESM modeling? The theory is that the fresh SOA photolizes rapidly, but the rate falls to near zero as aerosol ages. So we give a simple fix. We turn off the JSOA once tropospheric air age exceeds 50 days, and it substantially improves the stratospheric organic aerosol abundance in CESM. And thank you, everyone. Happy for taking any questions.
Yeah, very, very nice study, and thanks so much for presenting this. I have a question. I think I asked you before. We have the extended VBS scheme in the model where we divide between biomass burning, anthropogenic, and so on. So the main issue is in the stratosphere, UTLS region, right, in the photolysis rates. So is it possible to just apply it if you had the VBS extended to the biomass burning ones, or or will anthropogenic and biogenic VOCs, SOA also, usually they don't enter the stratosphere. But what a difference does that make? Have you looked into that version?
No, actually.
And in that version, by the way, we do use different photolysis rates for different species.
Oh, it's a great question. We didn't look at the VBS extend. Yeah. Yeah, it's quite interesting to know they have different photolysis rates. Yeah. Yeah. Thank you.
Great talk. I have a question about the photo bleaching. So would that change the interaction with radiation in the real world, and is that represented in the model, or do we need to change something in the model to represent like a brighter aerosol?
I think in the lab there were some studies shows that there are photo bleaching, but in general I think its uncertainty is pretty big, and for different aerosols they have different properties, and for some SOA, they have maybe 70 or 80% of the organic aerosol doesn't have photolysis. It's photo recalcitrant organic aerosol, but for other SOA, they have maybe 20% is not be photolized. So I think it's a little bit complicated to present it in the model.
Any other questions?
Jen, nice talk. I was just going to ask, the questions from Simone and Rebecca made me wonder, have you looked at impacts on OA in the upper troposphere? Or
yeah. Great question. We actually look at that because we changed a little bit photolysis rate in the troposphere. So we finally find our simulations doesn't make it worse. And in some case, for example, the South Hemisphere, and maybe our strategy makes a tropospheric organic aerosol simulation even a little bit better. So, yeah.
I think we should move on to the next talk. Thank you again. So next presentation is given by Hope Hunter, and it is on detection and classification of polar vortex disruptions using topological data analysis.
Hi. So I'm going to discuss mostly an algorithm that I created as part of my visit here and dissertation for detecting and classifying sudden stratospheric warmings. So let's introduction. The polar vortex is a low pressure region of high speed cyclonically rotating winds in the stratosphere, typically polewards of 50 degrees north, but it can be disrupted by planetary waves causing the winds to break apart, a warming in the stratosphere, and then a kind of displacement or splitting of the cold air, which was once encased. On the bottom right, I have an animation of the winds of kind of a typical sudden stratospheric warms. And biases in models have been proven difficult to get the climatology of sudden stratospheric warmings correct. So my presentations, unfortunately, often come with a bit of math. Topology, for those who aren't familiar, is the idea of spaces invariant under transformation. So you take a shape, and no matter how you stretch it, twist it, it stays, the properties that stay the same is its topology. The donut mug animation on the right, this is a pretty common topology joke that the mathematician can't tell the difference between his donut and his mug of coffee because they are topologically invariant. Some terms that we need to know to get through some of these ideas, Beatty numbers. So this is the number of connected components, rings and tunnels, and voids and cavities and shapes. We don't really see Beatty 2 in these polar vortex features, but worth knowing anyway. The idea of persistent homology. So you see this field of dots, and we pick thresholds, expand upon these dots, and it starts connecting and forming shapes. These are our Beatty numbers. In the case of models and reanalysis, we already have a kind of fixed grid where these things are located. They are topologically cubes, so we create a cubical complex. In this way, we kind of already know how things are connected. We use in this algorithm a discrete Morse style merging. So I'm not going to get into the math of that, but the idea is that this is going to clean up kind of small and insignificant features, determine how these things are connected. We use watershed segmentation to look at the boundaries between these points in space and determine where kind of the sharpest contours are. So this is a two-step algorithm, the first part definitely being the longest. This is a physically informed topological data analysis. So we are searching first on the raw field of data for low geopotential and separating the easterly and westerly wind speeds to make sure that those don't mix. So we first get a threshold of the field itself. We expand around it and then compute some topological operations to see how these things are connected, find the sharpest contours, and then determine the Beatty numbers from that space. The second step is the actual classification. This is a separate algorithm that took a lot of testing. We go through every day from a winter season starting 1st of November through the end of April, and we're looking for warming. So we use the WMO definition here, where it's 25 degrees Kelvin anywhere in the stratosphere, or below 10 hectopascal, it's 30 above 40 for a major warming. So those are the classifications. We search through the time series in a 3D space, did some hierarchical clustering to try to figure out how much warming is actually needed for the disturbances to occur. Found that a 10 latitude, 30 longitude, and 4 kilometer height worked pretty well at identifying the actual warmings. So we searched combinatorially, actually going 5, 30, and then every pressure level is saved individually to find in space where warming occurs. We also identify other states in here when we have a strong connected vortex, when we see geopotential disturbances, the early and weak season, which we don't really count in classifications. They're kind of early forming or they're already taken apart. There's a separate sequence to identify a warming, whether it is major or minor, and the type of geopotential disturbance. In the classification of warmings, we find 2 new kind of classifications. One of them is not so new, that aren't typically identified by other algorithms, one of them being a mixed event. This is in literature where we have multiple morphologies within the same disturbance, where they do not reconvene between. And the other one being a partial split, where the vortex splits but not all the way before it reconvenes. So I have a lot of visualizations now. Here's an example of a partial split. So we see at the upper pressure levels, we still have a coherent westerly jet, keeping that portion together. But at the bottom, it breaks apart. So we never see this particular event reconvene. But depending on which level you look, you could classify this differently. Here is an animation of one event that is not identified by the typical algorithm, looking at 10 hectopascal and 60 latitude. So this contains multiple events. We start with a partial split at the top, a minor warming, then we have a weak recovery, and then this turns into a mixed event. One of the interesting things about this particular event is that it is one that has a westerly ring and an easterly ring in the same vortex, with the easterly actually existing above the westerly jet coherent below. And this is another event we find. This is a minor displacement. It's a pretty typical one, but it's followed up by a strong reconvening of the vortex. That is the state we consider strong. So some things that we find in the numerical analysis is that the coverage of that canonical ring is actually kind of sparse. So if we were to only look at that area and look at easterly jets to identify a warming, we might miss a lot of events because the actual easterly winds are not located there. The same being with the westerly jet. There's a lot of time when it's not actually located in that region, the full contour. So here's some analysis of where we find easterly rings in these warmings. It looks like 4 major warmings. A lot of these easterlies are actually way further up in the atmosphere. Partial split being further down, and then the mixed and split closer to the kind of 10 hectopascal. And this is pretty consistent with some other recent literature that's found that we maybe should be looking further up in the stratosphere for easterlies. On the right, I have major and minor. There are 8 minor events in this detection that actually found easterly rings. These are quite spread out. And for the major, we see this peak kind of further up, as I said earlier. I didn't put this in a slide, but I should have, so I wrote it on my hand. Using the old algorithm, there are 30 major warmings detected over this 80 to 25 period. Our algorithm finds 73. 2 of the major warmings detected at the Charlton-Bufani algorithm are actually end of season. The vortex is no longer coherent, and one of them is actually one very long event that is counted twice. So it talked about I wish there was a timer on here. Cool. Talked about persistence a bit, how strong this thing is. So we find that persistence has a higher correlation with the jet stability than the wind speed does. So it's a much better measure for looking at when we have a strong, stable jet. And it is also better for the actual detection then of warmings when that breaks apart. Persistence also declines over a season pretty steadily, strongest in the upper altitudes in November and December, and then barely present in April, reasonably. We also find that the location of the jet core is changing throughout a season. So the latitude, it typically moves inward, and we see a lot more variance in the altitude, moving further toward the troposphere. Here's just showing the average descent of this core over the 45-year analysis. There is very infrequently a stable jet in April, which is why that looks so wavy. Also, the location of where it warms is associated with the event type. So the minors are typically further in toward The pole majors warm further out. We also see that it's pretty consistently in this kind of longitude region. This also tracks with the geopotential centroids from analysis. And as I discussed earlier, the displaced events, typically we see the rings further north in altitude, so it makes sense that the actual warmings are further north for displaced than split. So this is old analysis, it's an old algorithm, but I had tested this on Wacom 6, and here we see an event that's not detected. We see that 10 hectopascal, 60 latitude ring, and the jet, the easterly, does not form there, but we do see a split of the vortex. So how does this apply to CESM? I believe that we can use this algorithm to improve our model evaluation. Examining the polar vortex is a very dynamic feature rather than just this 2D level. So within each season, we find a lot more events and variability. So what this means is we might need fewer model runs to compare the climatology and variability between models and reanalysis. We also find these new events of mixed events and partial splits. So a more comprehensive evaluation of variability can be tied to the morphology. And as far as forecasting, this might be able to be used to find patterns in the jet position as a precursor to the events, the location of the easterly winds associated with magnitude, and temperatures typically indicate warming long before the wind disturbance, so we can get a better idea of the duration of the event. Thanks.
Time for some questions.
That region is sort of shifting southeast in our event tracking results, and so that would be consistent with an increase in atmospheric erosion in California. So we're trying to build this sort of connection.
Yeah, I think this is very interesting to compare to our model. And one thing that I was thinking, you showed most of the splits in the upper parts, while for ozone, I mean, it's important to look like between 25 to 20 kilometer where you have mostly the ozone loss occurring or up to. So yeah, I think the statistic, you can see a lot of split up also in the lower parts, if I understand, even though you didn't show it.
The kind, yes?
You said that most of the diagnostics apply to the upper part of the vortex. That is different.
Yeah, the
from
splits were more often identified by warming and easterly location further and lower altitudes, while the displacements were typically found further up.
Yeah, it would be definitely interesting to share some runs that we are doing right now and look at them. Thank you.
So.
Really interesting. Are you going to look at the southern hemisphere?
Hasn't been a thought yet. My dissertation was all Arctic, but sure, can do that next.
I understand the difference in the number of events is partly the height that you consider. If you look at just, say, 10 hectopascal, you get a quite consistent number of events with kind of the previous definitions.
Yeah, I read that off my hand earlier, sorry. So that level, it was the 30 events over that season, although 3 of them were fake. And we found 73.
Okay.
Consistent with other literature, we found about an even number of displaced and split major events, which is cool, although about half of these split were not fully disconnected. They were partial splits.
Okay, thank you. If there's no more questions, thanks you again. So next talk is given by Eva Bednars, and it's on the stratospheric ozone projections under sulfur-based stratospheric aerosol injection.
Hi everyone, I'm Eva. I'm a research scientist at CERS at CU Boulder and NOAA Chemical Sciences Lab. And long title, I'm basically going to talk about potential impacts of climate intervention on stratospheric ozone. Does it work? Awesome. So just to say, the results I'm going to talk about come from a study that was published as a preprint earlier on this year and is still under review for ACP. So if you're interested, you're welcome to refer to it or just talk to me afterwards. So we know stratospheric ozone is important. It shields us, life, and ecosystem on Earth from the harmful solar UV radiation. We also know that both human activities, but also natural processes have been driving significant changes in stratospheric ozone over the recent past. And as such, future projections of stratospheric ozone continues to be the subject of vast international research. And so far, until now, the leading anthropogenic drivers of stratospheric ozone changes studies have been the emissions of halogenated ozone-depleting substances and other ODSs, but also the greenhouse gases. But this research is now expanding to include the impacts from the so-called solar radiation modification or methods, or otherwise known as climate intervention or geoengineering methods. So these are potential methods to offset some of the risk produced by anthropogenic global warming. And there's a number of such methods, and one of the most commonly studied one, especially in the ozone context, is stratospheric aerosol injection. So it relies on the injection of aerosol precursors into the lowest stratosphere. Usually we are talking about sulfate aerosols, so injection of SO2, and all of that in order to reflect a small portion of the incoming solar radiation and hence cool the surface climate. Now, this could be potentially important for stratospheric ozone for two ways. First of all, if you put aerosols into the stratosphere, these provide active surfaces on which heterogeneous chemical reactions can occur that matter for ozone chemistry. And secondly, stratospheric aerosols, especially sulfate, they don't just reflect incoming solar radiation, but they also absorb in the infrared, and hence they hit the lowest stratosphere where they reside. And this is important, as if you perturb stratospheric temperatures, they can alter stratospheric circulation and affect ozone transport. So I want to look at how SAI affect our current stratospheric ozone projections using the new GeoMIP experiment called G6 1.5K SAI. So it follows the middle of the road SSP2 4.5 greenhouse gas scenario. In this case, SAI starts. Does the pointer work? No, too complicated, sorry, never mind. So in this case, SAI starts in the year 2035 with SO2 injection at 2 latitudes in the subtropics at 30 degrees north and south. And importantly, the amount of injection is adjusted interactively on runtime to keep global mean surface temperatures at the levels corresponding to roughly 1.5 Kelvin above pre-industrial, and this is consistent with the pledges of the Paris Agreement. And because models differ in terms of both their climate sensitivities to rising greenhouse gases, but also to the SO2 injection themselves, they both see the different levels of greenhouse gas-induced warming on the left, and then different amounts of SO2 injections that are needed to offset this different global warming. And so far, there have been 3 models that participated that have interactive chemistry on sulfate aerosols, CESM2 WACAM, MIROC Chaser, and UKSM. So here are the annual mean ozone responses to SAI simulated in these 3 models. So we see some, just eyeballing the plots, some overall similarities, which is good. We see, for instance, in the tropics, all 3 models show increases in ozone in the tropical low stratosphere. And these are dynamically driven. These are driven because sulfate aerosols hit the tropical low stratosphere, and this in turn decelerates tropical upwelling. And then outside of the tropics, models also agree in a way, like they do see all 3 models show decreases in lowest stratospheric ozone in the mid and high latitudes. And these arise primarily because of the heterogeneous halogen activation of sulfate aerosols and the resulting halogen-catalyzed ozone loss. Now, these were the similarities, but you can also see that the models do differ considerably, especially in the magnitude of some of the responses, and this will have a knock-on effect on the projected changes in total ozone column, so the vertical integral of the ozone changes. Okay, so what does such an ozone response to SAI and its uncertainty means for the long-term evolution of ozone? The plot here shows the time series of global mean total ozone column from present day, more or less, so 2030 onwards. So the dashed lines are the control ozone projections in the control SSP2 simulations without SAI in each of the 3 models. So as expected, all 3 models show increases in total ozone column over the course of the 21st century because of the reduction in halogenated ozone-depleting substances and increases in greenhouse gases. And we also see that even though the models agree on the sign of the response, they actually differ strongly on the magnitude of this projected ozone recovery. Now, once SAI started in 2035, all 3 models show a decrease in global mean ozone within the first few years of the deployment. However, after this initial drop within the first few years, ozone continues to increase over the course of the 21st century. It just remains lower than the ozone projected in the no SAI case. Now, another way to look at this is looking at the differences in the ozone between SAI and the SSP2 simulation, so the difference between the solid and dashed lines on the left. So we see all models show ozone reductions of a few Dobson units that tend to be larger earlier in the century and then decrease with time, but we also see differences, some differences across the models. Now, remember, these models have different levels of greenhouse gas-induced warming that are being offset with stratospheric aerosol injection, and these require different levels of SO2 that is injected. So what I want to do is take the ozone loss simulated in each model and scale it with the magnitude of the SAI-induced surface cooling. So I do it for an example period in the mid-century, so 2045 to 2064. And what we find is that the models agree remarkably well, all showing around 4 Dobson unit global mean ozone loss per 1 Kelvin surface cooling being offset. Now, this was for the mid-century. I can do the same thing for the later part in the century. And what we find is that this normalized ozone loss now becomes consistently a factor of 2 smaller than earlier in the century. And this reduction occurs in the normalized ozone loss occurs because of the ongoing decrease in background stratospheric halogen levels that are being available for activation on aerosol surfaces. And what that basically means is that the potential of SAI to deplete ozone decreased over the course of the 21st century. And this offsets the progressively larger SAI injections that are needed to offset the global warming and maintain surface temperatures at the target level. Now, the next question I want to ask is, how does the new results compare with the results of the previous GeoMIP experiment that was called G6 sulfur? And we find that the previous results were actually very, very different. And so in particular, the old G6 sulfur models all project increases in global mean ozone under SAI, which is shown on the right. And this basically contrasts strongly with the ozone decreases in the new G6 1.5K SAI experiments. So the question is that because the models used were different? I think the CSM version actually was the same, but the others models were completely different. The other potential reason is that because the underlying greenhouse gas scenario was different, so the previous G6 sulfur utilized the sort of business as usual SSP5 simulation, and then the new GeoMIP experiments utilize the middle of the road SSP2 scenario? Or is that because the injection location was actually different between those two GeoMIP experiments? So G6 sulfur injected SO2 at the equator, and G6 1.5K injected at 30 degrees north and south. So the answer here is that it's primarily the latter. It's the location of SAI injection that matters for ozone. So here I have the results from some older CSM2 simulations which systematically use different location of SAI to achieve the same level of global mean surface cooling. And we see that for injection in the subtropics and high latitude, so this is the green and blue dots, we see that those SAI simulations drives ozone decrease with time. And this agrees very well with the G6 1.5K SAI simulations on the left-hand side. And now for the injection at the equator, which is the red dot, and or injection in the tropics, 50 degrees north and south, which is the orange dot, both of those SAI strategies drives increases in global mean ozone under SAI. And this in turn agrees well with the G6 sulfur results on the right that injected at the equator. So basically, we not only see that there was a contrasting results in the 2 generations of GeoMIP experiments, but we can actually explain this to the different choice of SO2 injection that was used by the experimental protocol. Now, this was the global mean ozone response, and obviously the results were differ depending on the exact region in question, and I don't have time to go through all of them here. But I do want to finish briefly looking at the changes in the Antarctic during springtime, and this is the region that people are normally most interested in. So on the left, I have a similar time series if total ozone column changes, but this time in the Antarctic during spring. And then on the right-hand side, I've got the Antarctic springtime total ozone column loss normalized by the corresponding global mean surface cooling. And we see that, yes, SAI also drives Antarctic ozone, SAI also drives ozone decrease in the Antarctic during spring. And however, unlike it was the case for the global mean ozone, where the models actually agree relatively well, we do see a significant difference in the magnitude of this Antarctic ozone loss. And this is both the case for the total ozone column on the left and the absolute ozone column change on the left, and the response normalized with the global mean surface cooling on the right-hand side. And especially for the normalized ozone loss, we actually see a factor of 4 difference in the response, which is a huge uncertainty. And this highlights some of the still prevailing modern uncertainties in some of the SAI impacts that remain to be addressed. And nonetheless, one robust result remains that the normalized ozone loss, so the potential of SAI to deplete ozone, that becomes a fact, decreases as we go from the late century, as we go from the mid-century to the late century. There's also a decrease around the factor of 2 decrease in the normalized ozone loss. And this is because of the concurrent reduction in background stratospheric background halogen levels. And how am I doing? Okay, just very briefly, coming back to the uncertainty in the Antarctic ozone response to SAI, there are obviously many potential drivers of such uncertainty. And I just want to finish highlighting one potential contributor, the associated uncertainty in the dynamical response. So I mentioned earlier, SAI drives heating in the tropical low stratosphere. That in turn forces strengthening of stratospheric jets on both hemispheres. And when we correlate the magnitude of the springtime Antarctic ozone loss on the y-axis with the corresponding changes strengthening of the polar vortex on the x-axis, and I do it for 3 models and 2 time periods, we find we actually end up with a pretty strong relationship as far as relationships in the stratosphere go in general. And notably, this ozone vortex coupling goes both ways. So it's not just that the polar vortex strengthening drives Antarctic ozone reduction, but the Antarctic ozone reduction itself also causes polar vortex strengthening. So there's this 2-way coupling, and the causality can't be fully inferred. However, this kind of strong relationship does offer a potential to hopefully help constrain some of the uncertainty in the model responses. Okay, so just to summarize, I'll talk about stratospheric aerosol injection, how that affects stratospheric ozone, but can affect stratospheric ozone via changes in chemistry from heterogeneous reactions on aerosol surfaces, and also dynamical changes from perturbation in atmospheric temperatures. So I talk about the results of the new GeoMIP experiment called G61.5K SAI, and how the models participating in it show decreases in global mean ozone of a few Dobson units. And this result was very much different to the results of the previous GeoMIP experiment, G6 sulfur, which showed global mean ozone increases. But the good thing, we actually managed to pinpoint exactly where this difference is coming from. It's coming from the different location of SAI used in the 2 generations of GeoMIP experiments. I've also talked about how the potential of SAI to deplete ozone decreases as we go into the later in the 21st century because of decreases in background stratospheric halogen levels. And I also talk about large spread in springtime Arctic ozone responses that remains to be addressed. And with that, thank you for your listening.
Any questions?
Hi, thanks for the great talk. I'm just wondering if you have looked at or are planning to look at alternative aerosol to inject, like heavy metals, for example, which might have a different effect on the ozone loss.
Not me, Simones. But yeah, alternative aerosols has been looked at in the context of SAI to reduce the stratospheric ozone depletion, so reduce the heterogeneous reactions that happen on aerosol surfaces, and also reduce the stratospheric heating that would also reduce the dynamical responses. This is not something I've been looking personally. I know colleagues at NCAR, Simone and Ilaria has been looking at this, and also colleagues at other institutions like ETH in Zurich.
If not, we'll move on to the next talk. Thank you again. So next presentation is given by Maria Valmartin, and it's on the development and application of a UK regionally refined Musica configuration.
A cursor, or there is no...
you can use this one.
Okay, perfect. Okay, yeah. Okay, just wanted to, okay. And to pass the slides, sorry, it's this one? Sorry, okay, perfect. Okay, thank you. So we are just moving now from the stratosphere, from global scale to surface level, and also to a regional domain. So I'm at University of Sheffield, but in September I will be joining the Polytechnical University of Valencia. So I'm moving to Spain, so warmer and sunnier climate. And of course, this work is not just upon myself. So it's a collaborative work between University of Manchester and University of Sheffield, with lots of support from NCAR as well. So I want to give you a quick overview of the Musica development that we have done across the two institutions, and also a couple of examples. So why do we need Musica in the UK? Well, the UK is a country that is also, the air pollution is being affected by domestic sources, but also a lot of pollution from continental sources from Europe, and also from, we are downwind from the US. Also, it's a small country. So just to give you an idea, it's the size of Wyoming. So, so we need really a tool that allows to resolve chemistry at really high resolution. So we have been developing, we joined the Musica wave, and then we developed a grid across the UK. So we developed this 7-kilometer grid, and this is work done by CG1 and James Keane, who's a collaborative work with a lot of support from NCAR as well. And then, so what I want to talk to you today is actually to give you an overview of the grid and validation that we have done. Also, so 2 applications, one on biomass burning and another one on enhanced weathering, and I will tell you what enhanced weathering is. Also talk a little bit about what things that we have learned along the way, so strengths and limitations. So these are the 2 examples. One is on biomass burning. So we look at the air quality impacts of biomass burning, global biomass burning in the UK. We ran Musica, or the UK Musica, in 2018 there. We used the TS2 chemical mechanism. So we added the isoprene and terpenes, oxidation, and more complex chemical mechanisms. And we used the array of emissions. So CAMS, anthropogenic, FIN, and Q-FED for biomass burning, and we had meganon. And we ran 2 experiments, biomass burning on, and another experiment or control, and then an experiment with no biomass burning. The other case was enhanced weathering. We ran the year 2022. In this case, we used the TS1 with Mosaic, with the nitrates. We ran with, well, one was with MERA2. So there are 2 different cases, but just with the same application in the UK with GEOS5. We also use CAMS for our anthropogenic emissions. We also added soil nitrogen emissions from CLM5, and we ran 2 simulations, one with weathering and another one without weathering. So actually, these are work done by 2 PhD students, one in Manchester, CG in Manchester, and Katie in Sheffield. And we also run actually UK Musica in 2 different HPCs. Archer 2 is the HPC funded by the UK government, and then we have the ability to run that in Derecho. So we have UK, the grid in the 2 different, computers, supercomputers. So just a quick validation of Musica for the year 2018. We use actually the Met Office reanalysis and also the Department of Environment site observations, but I'm showing here only the comparison from, I was told to do it here. Okay, it just appears over there as well. So this is surface ozone. So you can see that actually Musica in the UK captures well the gradient of surface ozone, or the variability of surface ozone. We are slightly overestimating surface ozone. PM2.5 is a little bit different, but we have a good agreement over the northwest part of the country, and then we are underestimating PM2.5 in the southeast part of the country. And that can be because we don't have nitrates in this configuration, but it might be also some uncertainties of European emissions, or also transport from Europe, especially during the springtime. This work actually is under review in JJR atmosphere. So CG also went a little bit beyond this analysis, and then he wanted to look at the added value of having this refined grid in the UK. So it's a little bit difficult to appreciate what we have here, but here we have the UK, this is the UK, and here we have Europe, and what we have here is a PM2.5 plume. So in this work, he compared the grid, the Musica grid, with a normal global grid of 50-kilometer run. So you can see that both grids actually picks the PM2.5 plume, but actually with Musica, we really resolve better the transport and the vertical mixing. And just to give you a little bit more quantification, actually CC compute the normalized spatial variability and actually improve actually the impact of PM2.5, or the resolving PM2.5 within the UK domain compared to the 50-kilometer resolution grid. So in terms of biomass burning, I'm showing here the changes in summer PM2.5 from biomass burning and the control, well, the no biomass burning run, and then with the summertime. So during the summertime, actually, the impact of biomass burning increases PM2.5 in the US, especially in the central part of the country. So it's about 10-15% increase. So we are talking about 1.5 2 micrograms per cubic meter. And surface ozone is a little bit more noticeable in the part of Scotland, on the north part of the country, which is up to 3.5 ppb. So on an annual average, actually, biomass outside the UK affects or increases 0.7 micrograms per cubic meter of PM2.5 and around 2 ppb of surface ozone. Of course, the impacts vary by the season and the strength of the transport. But I mean, if the UK actually is trying to look at to meet air quality standards, is something that they will need to take into account. So now let's move on to enhanced road weathering. So just in case it's not, just to give you a quick overview, this is a land-based carbon dioxide removal strategy. It consists of applying crushed silicate rocks like basalt to croplands, so it's to accelerate CO2 removal through weathering reactions. So one of the things that we are looking with this strategy is that we go it's not only sequestering carbon, but also changes the soil properties. So increases soil pH, also changes nutrients and the nitrogen cycling. And that affects actually the soil nitrogen emissions as well as VOCs. And so I have an infographic here. So if you change the soil nitrogen emissions or even VOCs, you also affect surface air quality. And see, this is one of the things that we are looking at the University of Sheffield. So actually with UK Musica, we can resolve air quality across the UK, but we also have all the land processes from CLM5 that allow us to have the changes in the soil nitrogen emissions. So before working on the air quality impact, we had to do some modifications in the nitrogen cycle in CLM5. It's a simple, well, it's not simple, it's really complex, it's really good nitrogen cycle. But it's a hole in the pipe, it follows a hole in the pipe approach. So nitrogen inputs come in and nitrogen goes out. So in terms of plant nitrogen uptake or nitrogen losses to the atmosphere. So for this work, actually, we implemented ammonia volatilization, we added nitric oxide, and we also link the nitrogen cycle to changes in soil pH, because weathering, or hence weathering, changes the soil pH. So this one was published in 2023. And now what we are doing is that taking some small piece of the code and soil nitrogen emissions and just put it in CESM 5.4. But this is another project. So just to give you a quick overview of the case 2 validation, in terms of, we use in this case CAMS reanalysis as a 10 by 10 kilometer resolution. And ozone and PM2.5 was really a good spatial pattern, is similar to what we found in case 1 or in the biomass burning example. In this case, we focus on ammonia and nitric oxide, and we have a good, actually, spatial pattern, but we are overestimating slightly the ammonia and nitrogen concentrations. So first, one of the things that we look at is how was the changes in soil nitric oxide and ammonia emissions from basal applications. So in this case, we run a scenario with CLM5 in which we apply basal to the UK croplands to remove 30 megatons of CO2 per year. So just to put that into context, it's about 45% of the carbon dioxide that the UK government will need to remove by 2050 to reach net zero. So it's not a massive scenario, but it's not trivial. So we are trying to help the UK government to remove about 45% of their CO2. So anyway, so just applying basalt on the UK croplands, we see that it will be a decrease in soil nitric oxide, so about 15%, and a slight increase of ammonia, so about 4% increase. And those increases and decreases are really localized where the croplands in the UK are. So that will change air quality, and this is what we did with UK Musica. So what are the changes in surface air quality? So can you see? Yeah, there you see the color change. So this is we are still analyzing the data, but one of the things that we see during the springtime from the weathering and no weathering. So the run with soil nitrogen oxides and no without the changes in soil nitrogen oxides, is that there will be a consistent increase in surface ozone during the springtime. And the reason, I mean, just to remember that the UK is nitrogen oxide saturated, so a small decrease in NOx actually favors the ozone formation. It's not large, we are talking about 0.5 ppb. With PM 2.5, we see a little bit more, not less consistent. It's a mixed response. And we remember that we also have decreases in nitric oxide, decreases in nitrogen oxide, increases in ammonia, so there might be some competing effects on the secondary aerosol formation, especially on ammonium nitrate. Or one of the things that we are also finding challenging is to interpreting the results, and I will tell you a little bit about this challenge. But anyway, we find similar patterns across other seasons, but actually the signal is a little bit less conclusive. But this is the challenge that I wanted to mention. This is nothing, I'm not showing anything new here. We know that from CAM6, but when we do experiments, especially these perturbation experiments, what you expect is that only the thing that you change is modifying the model. So like, for example, biomass burning, no biomass burning, or in case of weathering will be the soil nitric oxide and ammonia emissions. But what happened is that because we have CAM6 with the cloud aerosol feedbacks, we also get some small feedbacks on meteorology. And what we have here is the changes in surface temperature from the weathering and no weathering is small, but also loops into isoprene emissions. And so when we are dealing with these small changes in surface air quality or in any other perturbation experiment, these small changes might affect actually your results and make this make challenging interpreting the results. So anyway, this is my final slide. I don't know how am I doing with time. I'm okay. So we have our regional refined grid in the UK, and it's available in Archer 2 as well as Derecho. We found that actually biomass burning affects UK air quality through long-range transport of pollution. We also look at episodic wildfire events, but I didn't have time to show that, but I can show it to you. In 2018, we have a massive fire in the UK, the longest on record. So we look at that, how Musica actually was simulating the plumes from this regional or local fire. Enhanced weathering changes soil nitric oxide and ammonia emissions, and that affects air quality in the UK. We are still analyzing the data. And the key challenges that we have, and I don't think I'm saying anything new, is the computational cost. And I think for the weathering experiment, we ran it in Derecho and we pushed the ACOM resources a little bit too much. I'm sorry, Rebecca. And the other thing that we are having as a challenge is the attribution, because we have all these aerosol cloud feedbacks that affects affect some of the air quality changes that we are having with Musica. So the next step, so we are going to start looking at the nudging and see if we can just smooth that out. And also we want to keep Megan Megan off and prescribe the emissions. But again, these are computationally expensive simulations, so you don't have that much room for testing. So you need to go and run the simulations. But anyway, this is what we are working right now across Manchester and Sheffield, and we have the grids available for the community. So if someone wants to play with the grid or use the grid across the UK, we are welcome to add it on the GitHub. I don't know how. Yeah, I think there is a repository for grid. So yeah, well, happy to share all the resources that we have developed. Anyway, I take questions now and I shut up. Thank you. Thanks.
I think we can take maybe one question.
Thank you so much, Maria, for the nice talk. And thanks also for pointing out the just issue of noise, even when we're nudging. 'Cause I think that's something we've also, sort of been forced to reckon with a bit. My question is actually with respect to the nudging. When you go to this regional refinement, I'm wondering, are you still nudging to kind of large scale meteorology, or are you using any finer scale, and also just which variables, how strongly are you nudging? And I'm happy to talk offline. I
can
realize that's a
talk
lot of
you-
questions.
Yeah, I'll talk to you offline because this is simulations that Katie and she set up. But yeah, you nudge globally, but you also nudge regionally, as far as I understand, and you have different coefficients as well. So you can play, there is room to play. But yeah, so yeah, you nudge globally as well. Okay. Anyway, I'm going to be around, so if you guys have any questions, we keep talking.
If there's no more questions, we'll move on to the next presentation, which will be given by Ben Gobert. Yeah, we can thank. So Ben will present on an overview of emission-driven methane simulations.
Good morning, everyone. So this is a collective work funded by NOAA with a close collaboration with University of Arizona and NOAA GML in Boulder. This also work with in Spain and Argentina, where they developed the halogen chemistry, and Texas A&M. And we got the data set as well from the European CAMS project, and lots of observations from NOAA. This is part of a global, larger Earth system vision of improving prediction across timescales, and it's a larger NCAR thing, but here I'm adding the chemistry to it. We're interested in the interaction among Earth system components and improving those interactions and improving the connection between spatial and temporal scales, especially for physical and chemical processes, and having a better understanding and quantification of external forcings and feedbacks across the Earth system. So here's an example. The Earth system chemistry is multi-scale and coupled system. So here's spatial and temporal scale because of times, chemical lifetime of the species is spanning a wide range of spatial scales. And we are interested in methane, and methane is reacting with OH, which means you interact with all of the scales at the same time. There has been a wide variation in the methane growth rate, and people are trying to quantify it, but it's very uncertain. And we need to have a better understanding of geological OH to have a better understanding of how much methane is changing every year, as 90% of the methane loss is its oxidation by OH radical in the troposphere. There are also studies that are overestimating the impact of NOx, because if you just have emission scenarios where you change one of these species, you would have an impact on OH that is different. And this can have detrimental effect where you're thinking that reducing NOx will be actually increasing the methane lifetime, but it's actually a bit more complicated than that. But like we're trying to improve this understanding and having better mitigation scenarios. So OH is a very complex chemistry. It has a primary source from OH photolysis in the troposphere. And it's recycled through many reactions, as shown here, that important paper by Lelyveld in 2016. And then there was a review by Arlene Fiori and others looking at what is important for global mean OH. Not only the chemistry is complicated, but the sources, as we just saw, agriculture, fossil fuel, but also wetland methane, vegetation and fires, lightning NOx, they would all contribute to sources and sinks in a coupled way. In fact, if you compare geoschem, simple chemistry, and MCM, OH is the most important species of the system. The issue is that we don't have any good observational constraint aside from the decay of messy chloroform and some others HFCs. But that only gives you a global maybe hemispheric annual mean estimate of the OH, and so therefore the methane loss for that value. And so then we know that the tropospheric chemical lifetime of is 11.2 years. And it's estimated to have 10% uncertainties with a small interannual variability. So we know those things from the so-called proxy methods. Here I'm interested in using Earth system chemistry models where you couple radiation, dynamic chemistry, and those emissions of forcings to interactively and prognostically estimate the full photochemistry of tropospheric system to estimate OH. But then you have biases and around 20% uncertainties, and so we're trying to reconciliate those two estimates. And here I'm advocating for the advantage of resolving physical and chemical processes across timescales is advantage of Earth system chemistry models, and that we can improve them to better represent OH. But still, it's, you know, last chapter of the IPCC is saying that this is a very important issue to tackle. And why is that? Is that even if you get only 4% variability in every year in OH, you could have, I don't know if this is working, you can fit a positive trend or a negative trend. So we don't know about the trend in OH, whether it's from models at the top or from the messy chloroform estimates at the bottom because of those large uncertainties. And models respond to increasing NOx and CO and ozone to have an increasing source of OH and a larger OH over time, but the messy chloroform doesn't really support that. But then the interannual variability came back as an important thing during the 2020 COVID lockdown, where we got like extreme reduction in NOx emissions, which drives the OH down, but also Australian fires and other things, including strong reduction in ozone. And so here are just 4 papers, but there are many more. But the Chu et al. Is estimating that only 14% of the methane growth rate is due to OH in 2020. But the other 3 are estimating a role of OH that is more than 50% of the methane growth rate. Knowing the importance of methane emissions, this is a very important statement for methane budgeting. So here we're developing emission-driven methane simulation of mainly CAM-CAM at the moment, but hopefully with a full emission-driven CSM in the future. We want to include and quantify the chemical feedback. We want to evaluate the chemistry and the chemistry changes on the methane growth rate, and eventually having feedback on emission processes within the Earth system, so fires, soil NOx, and wetland methane in an interactive fashion with our improved chemistry system. So we have published a paper describing our inclusion of the SLH will help us reduce the bias in tropospheric OH, increasing the methane lifetime by a year and decreasing the feedback factor with respect to OH. So in this setup, we have more chlorine and less OH, and it's improving methane and other related species such as CO. The biases are much reduced and is allowing us to have a reasonable emission-driven methane simulation. So Xuan Feng has been using, I don't know if I, yeah, so this is supposed to be a video, but Xuan Feng at Texas A&M has been, we've been implementing methane tags to look at regional impact of emission, and then we can calculate it's the one to the left, if you click on the left figure. so you can see the different lifetime in here, where we're using the European, Asian, and American tags to look at their relative efficacy on the methane concentration. And it shows that you have different concentration from different regions, but it's still only at the mixing ratio state, not from the radiative forcing standpoint. But emissions in Europe would linger longer in the higher latitudes and thus have a longer lifetime. They're also looking into the sensitivity parameters, the feedback factor, looking at the sensitivity of the methane lifetime to the methane burden. And so far there is no huge differences compared to the state of the literature. But we can do this sort of perturbation where we have no methane emissions, or 75 or 125% of the baseline emissions, and look at the impact over time. So now we're looking into long 20 years simulations. And so here is two different sort of drastic scenarios, one with very high CO emissions from MOPIT inversions versus the CMIP7, which have less emissions than for CO than CMIP6. The fire is driven by FIN in one case and the CMIP7 emissions in the other case, where FIN has much higher emissions in the beginning of the period and a strong decreasing trend. And the NOx have different trends in the beginning of the 2000s year, where the CESM emissions are increasing and then decreasing in a strong fashion. So this is giving us a sensitivity to chemistry emissions on OH. We did also runs with ERA5 methodology and MERA2 nudging. And the lightning NOx is slightly different, but overall, on average, similar. But except for the last 3 years, where the ERA5 has less lightning driven, there is less driving in CapChem driven by ERA5 as opposed to MERA2, which has important implication for OH. The biogenic emissions are higher when you're using ERA5 because of higher temperature in the tropics. But overall, the seasonality and interannual variability is similar. But then if you look at the right here, we can then quantify the differences in OH between those two simulations are the combined different effects of emissions and methodology. And so you can see with the black line that the model growth rate is very well simulated in both simulations, but with some slight differences that we can now analyze. So for instance, the role of methodology at the end of the period makes the simulation driven by ERA5 to have a much higher methane because there is less lightning emissions. So we did regressions and we're trying to, so first we do use the Chu et al. Where we're taking into account the relaxation of methane. So we're looking at differences in emissions, relaxation back to steady states, and changes in OH for every year. And so you can see here, for instance, the 2011, the CSM methane simulation will have 4 ppb of methane due to OH and corresponding to 30% of the methane growth rate. And then in the other one, it would be 4.6 ppb and 32%. So in this case, they agree about 4 ppb and 30% of the methane growth rate that is due to here a positive OH anomaly. So it's a reduction in methane growth rate. 2015 was a negative OH year. And 2017 was the most positive anomaly of the record. So in those cases, they sort of agree. In 2021, one simulation has a strong negative anomaly, but the other one is positive anomaly. You can see that 2020, they agree that it's not that important. It is only 20% or 13% of the methane growth rate that is due to OH. So that 14% agrees well with Chu et al. And 2003 was a negative OH anomaly. So they are around 30% on average of the methane growth rate is due to OH, with sometimes higher values, but most of the time lower than that. In terms of percentage, if you look at the beginning of the period where the methane growth rate was small, then obviously the relative contribution is more important. Then we did regression by zonal band with many different forcings and burden. Here I'm showing the forcing, so surface NOx emissions, fires, and anthropogenic CO sources, and then natural emissions and methane emissions. And you can see that there are some common features, like the reduction of surface NOx in 2020 during COVID in both emission scenarios, but the one with CMIP7 emissions did not really recover, so you have negative NOx anomalies, which gives you negative OH anomalies. You can see the NOx trends that are differing in the beginning of the period are responsible for slightly different contributions, with NOx being more important in the CMIP7 3-month simulation. The fire CO from FIN that are decreasing are causing an increase in OH over that period, with some contributions from biogenic emissions. Biogenic emissions are usually pretty important and sometimes overlooked in these sort of studies. Here in 2015, where El Nino at larger temperature gives you more biogenic emissions, it can be an important contributor to the negative OH anomaly for that year. And the fire CO are also important in both cases. So to look further into the impact of dynamic, we did an ensemble of 30 different nudging. And so that allows us to look into the tropospheric ozone versus methane lifetime paradigm. And so there are some nonlinear effects with changes in clouds are changing lightning and ozone production, but the ozone production is depending on the actual methane emissions that are also changing because of the temperature effect of the dynamic ensemble. There is a Schuo's poster is upstairs if you want to have more information about this. And we also look at chrysisoprene and troponyl-formaldehyde to further evaluate if our OH or the sources of biogenic emissions are responsible for the biases in isoprene formaldehyde and then CO and methane down the road. So OH is very important in our system model to estimate the methane variations with large uncertainties due to external forcings and feedbacks due in natural emissions such as lightning NOx and biogenic emissions, and halogens are playing a role in reducing buffering the OH to perturbation. On the other hand, methane play a relatively small role in the OH variation, which means that prescribing methane could be good enough for looking at single-year tropospheric chemistry budget. But then you can have simulations with different meteorology and emissions and having a very similar global OH, and so you will have the same methane simulated, but for completely different reason. So we really need more model intercomparison, and yeah.
I think in the interest of time, we move to the next talk. But if anyone has questions for Ben, please find him during the break. So we will have our last talk for this section, which is given by Ying Xiao Zhang, and it's on the advanced global scale pollen emission modeling in an Earth system model.
Okay, perfect. Let me just test if I can control. Okay, perfect. Hello, everyone. My name is Ying Xiao. I'm an ASP postdoc at NCAR. Today, I'll talk about our recent research about incorporating pollen inside the CESM framework. So some background information. Primary biological aerosol particles are emitted from Earth's biosphere, and after that, they can participate in the atmospheric process. And among all of them, I'm mainly interested in pollen for this work. This is the pollen emission video, and this is from the wind-pollinated species. This type of species rely on wind to carry their pollen long enough to reach another species, another plant to finalize the fertilization. Because of that, they can produce tons of pollen every year, as shown in this video, and that pollen can stay in the atmosphere for a long time. So as atmospheric scientists, we are interested in the wind-pollinated pollen. After emission, this type of pollen can impact solar radiation. They can also be lifted up to the upper atmosphere and impact cloud formation and precipitation. One thing to note that is that pollen is one of the biological aerosol particles, so they can nucleate ice at warmer temperature. So recently, they have been drawing more attention. Another part of pollen that has been drawing a lot of public attention is that changing pollen season and magnitude. Over the United States, warmer temperature has been driving longer pollen season everywhere, and higher carbon dioxide can also impact the plant photosynthesis, make plant grow bigger, therefore impact pollen production. In the right part, this is a chamber study. When they doubled the carbon dioxide concentration for the grass, they saw over 3 times higher pollen production. So all of this would worsen the future allergy season. So this kind of change has been frequently in the news. So as I have been mentioning, pollen can be important for weather system or public health. So it should be one of the important factor we consider in the Earth system modeling framework. However, currently we do not have a good tool for that. There's no global model for pollen that realistically reproduce pollen concentration for large scale. So currently, we think it's the time to incorporate pollen inside Earth system models. Other than Earth, ECMWF is also doing something similar. But anyway, this study would be one of the first, and we think it can be a big step in our field. The method based on the pollen emission model I developed during PhD at Steiner's group. Basically, this emission scheme is based on the observed correlation over the United States. And the first one is the production factors, where we are including different type of species pollen production, and this production can change with temperature or carbon dioxide. This is also driven by the land cover. Here I'm showing the plant functional type coverage, but this model can also do species level coverage. Last one is a phenology term. So here the colorful lines is showing the observed pollen concentration, and it basically fits in a Gaussian distribution. So in the model, we use Gaussian curve to represent this process. And the start date and the end date of pollen season differs for different species based on their correlation with the temperature. And the magnitude of this curve would be impacted by temperature, carbon dioxide, and precipitation. So Before this model is offline and driven by the climate variables, here we want to make it fully online to be coupled with land process and atmospheric process. The first step is to couple the emission model with the land model. Here we are using the CESM, and we are considering 5 different plant functional types. Ragweed is generally not included in the land model, but we just calculated it based on this, its fraction over urban and crop land cover. And if you remember, I have been keep mentioning that our pollen emission model is developed based on the United States observation. So how do we couple it into a global model? So very timely, I'm also leading a review paper that we are summarizing the global long-term pollen trend. And we are collaborating with co-authors over 6 continents, and we're collecting a lot of observational data to look at the pollen trend. Here I'm just showing the total pollen concentration change. This data collection process really benefits our global model development, but at the same time you can see that we do not have a lot of observational data coverage for pollen, and it's also mainly located in the North Hemisphere. So having the global level model can help us to fill this gap. When we're looking at the global pollen trend, we found something very interesting. Here, when the circle is showing the American and Europe, which are the 2 regions we have the most data coverage, and we looked at their pollen change. Here is 4 different species about their pollen production change in response to the warmer temperature, either decrease or increase. And I think it's very hard to see the lighter color, but the solid color showing here is the ones we have a statistically significant relationship. One interesting thing is, of course, we do say that different species respond differently to temperature. But something even more interesting is that when we look at Europe and North America for the same type of species, like here it's Acer is a maple tree, we generally say. It is decreasing with warmer temperature in Europe, but also increase in North America region. So because of this, it further motivates us to develop regional specific pollen parameterizations. Here is our simulated pollen emission flux for different plant functional types. And we grouped the global region into different sections for regional specific parameterizations. This parameterization depends on our data availability for this region separation, also depends on how that different plant respond. Overall, with this framework, when we look at the total pollen mass emission, it's around 60 TG per year, which is comparable to previous study estimates. Although it's still a small compared to other type of aerosol like sea salt or dust. But as I have mentioned, pollen is special because it impacts public health a lot. So it's definitely nice to have it incorporated in our system modeling. Afterwards, we transport the pollen emission from land model into the community atmospheric model, where pollen would be in the coarse mode of all of the aerosol and go through all the process for, along with other aerosols. And here I'm showing the final estimate total pollen daily average concentration. We see hotspot over the eastern United States or Central Europe. And this has been proven by our observational data. We are also seeing the hotspot like in Africa, which is driven by the grass coverage. Currently, we are almost done with this work. We are mainly working on tuning and evaluating. Firstly, I'm showing the evaluation over the United States, where we are comparing the climatological monthly pollen concentration for CESM simulation and observation for different sites. In general, our model is doing a pretty good job for capturing the magnitude and the seasonality, although pollen emission can have a large seasonal variation, but or interannual variation. But the thing makes me very excited is that before our pollen model framework has been incorporated in the regional model framework, it's part of the NOAA air quality forecasting. And this CESM model with coarser resolution, the result is actually very comparable with our high resolution regional model. So this is a good sign. And then we also compare the model over the Europe region. Because the data limitation, they are not allowed to share the raw data with us. So we are just using the annual total pollen concentration. And here the contour is the simulation and dot is observation. I'm showing the correlation for different type of species. Generally, we see very low correlation for grass, so that's gonna be our next main target for model tuning. And we are also currently working on the South Hemisphere, but generally, we think we are very close to get it done with like 1 or 2 months. And lastly, but most importantly, I want to acknowledge all of my co-authors. Danny Long is the scientist at ACOM. We discussed about this idea in last CESM workshop, and this has been the side project for both of us. But I'm very excited to see how it goes after a year. And I also want to acknowledge all of other co-authors for their contribution and support for this work. Thank you.
Okay, we have time for a question or two.
Very nice, thank you. One thing I was seeing is that over Africa, Sahara region, when you're not in the desert but below, there's a large amount of pollen in the model. Is that because of the temperature dependence, or why is it relatively large compared like to Canada or something where you would, or where you have a lot of trees and you would think there's maybe more pollen?
That's a really good question. Generally, we see more pollen production from trees other than grass. But somehow in the South Africa, we see such high grass concentration. One of the possibilities we're thinking is that all of our available sites are located in the South Africa region. So when we incorporate that in the model, like further like upper Africa, like close to the desert region, it becomes quite high because that correlation is dependent on the temperature. We don't know if it's right or not because we don't have any observation data over there. But yeah, currently we are just trying to tune with whatever sites we have available. Like having something is better than nothing, no information there at all.
So much for the interesting talk. I'm wondering if in Cam 7, if you've started to allow the pollen to interact with the clouds yet, and what that looks like, if you have?
Yeah, I love this question. Actually, I have been talking about this a lot with Simon, Danny, and other scientists in ACOM. Before we allow pollen to interact with cloud in WRF-Chem, and we developed the cloud macrophysics scheme there. We definitely want to reproduce this progress to incorporate that inside the CESM. So it's definitely something we want to do.
Okay, if there's no more questions, thank you again. And so now we will have a break until 10:45. And thanks all the speakers for staying on time.
Yep, let's start up again. I think we're ready. Yep, okay, good. Yeah, welcome back. Second part after the coffee break to our chemistry aerosol session. And we'll start with Arlene Fiora's group. And we have 3 presentations, and they will share the next 2 slots. It's a little different than in the agenda, but I think you guys will introduce yourself. But it will be first Stephanie Elkins, and then Xuan Yu, and then Arlene following in the end. But we will have questions after each of you guys' talk. Okay.
About 10 minutes, so if you could stop at like 10:15.
Okay, I will do. Thank you.
Great. Okay. Hi, everyone. I'm Steph Elkins. I'm a PhD student at submitted work estimating the avoided tropospheric ozone radiative forcing from U.S. air pollution controls. Before I begin, yeah, is it on? There we go, okay. Before I begin, I'd just like to thank my co-authors for their contributions to this work, as well as funding from NSF. Okay, so near the surface, ozone is a harmful air pollutant that is damaging to human health and ecosystems. It's formed via the reaction of CO, non-methane volatile organic compounds, and NOx in the presence of sunlight. When lofted into the free troposphere, ozone plays another important role as a greenhouse gas, absorbing and re-emitting long-wave radiation, in addition to its interactions with short-wave radiation. Since the pre-industrial era, tropospheric ozone is estimated to exert about a 0.39 watt per meter squared radiative forcing, as estimated by CMIP6 models from this paper in 2020 by Shi et al. This places tropospheric ozone as the 3rd most important anthropogenic greenhouse gas behind CO2 and methane. However, unlike CO2 and methane, tropospheric ozone is considered a short-lived climate forcer with a short globally average lifetime of approximately 3 weeks. Therefore, its distribution in the atmosphere and abundance in the atmosphere is highly spatially and temporally variable, and so is its associated radiative forcing. And so in our efforts to target ozone as a surface air pollutant, an important question becomes how might we be altering, or have we altered, the spatial pattern and magnitude of the tropospheric ozone radiative forcing? And specifically in this talk today, I'll focus on the avoided tropospheric ozone radiative forcing from US air pollution controls after 1970. Okay, so to get at this question, we simulate a world avoided by US air pollution controls using CESM2, WACOM 6. So this is the fully coupled version of the model with an approximately 1 by 1 degree horizontal resolution and 70 vertical levels, extending to about 140 kilometers. It has interactive ozone chemistry in both the troposphere and stratosphere. And so we use a pair of initial condition ensembles here, each with 13 members that were produced by some of our co-authors. The first is a historical ensemble, which uses CMIP6 historical emissions from 1950 to 2014. And then the second represents the world avoided by US air pollution controls, or we call it US frozen EF. And this scenario is approximated by freezing emissions factors at their 1970 levels in the US for reactive gases and aerosols from the CESM emissions inventory. These simulations go from 1970 to through 2013. So these 2 emission scenarios result in the following emissions trajectories of ozone precursors, CO, VOCs, and NOx from left to right, shown by for the US totals by the dashed lines here, and then for global totals by the solid lines. You can see that the emissions trajectories diverged in 1970 with the enactment of the Clean Air Act, and continue to grow over time in this world avoided scenario, instead of declining as they did historically. So by the end of the time period, emissions in this world avoided scenario of these ozone precursors are much larger. And so for the rest of the following slides, we'll analyze the results of this paper for the last decade of this time period, from 2004 to 2013. Okay. So from these simulations, we can estimate an avoided tropospheric ozone, the avoided tropospheric ozone by US air pollution controls for this last decade of the time period. So here I'm showing the avoided annual tropospheric column ozone in Dobson units, which is calculated as the ensemble mean difference between the world avoided and historical scenarios. The hatching here just represents where signal to noise is less than 1, where noise here is 2 standard deviations of a distribution of decadal internal variability that we sample from our initial condition ensembles. So you can see that the signal is robust to internal variability across most of the northern hemisphere. The signal is largest over the eastern US and downwind over the North Atlantic Ocean. We also can look at this signal in the annual mean, looking at the vertical profile. We see that the signal is greatest in the upper troposphere, where the lifetime of ozone is longer. We averaged the signal over 3 different spatial averaging regions: the eastern US and North Atlantic Ocean region, which is designated by that white box on the map, the northern hemisphere from 20 degrees and northward, and the globe. We find avoided tropospheric column ozone globally averaged of about 0.5 Dobson units. And just to put this into perspective, this is about 6 to 8% of the global mean pre-industrial to present day tropospheric column ozone change, estimated from ACMIP simulations in the Stevenson et al. Paper in 2013. Okay, so to calculate tropospheric ozone radiative forcing from this emissions perturbation, we apply an ozone radiative kernel, which was developed by Xi et al. In their 2020 paper. This provides a 3D gridded net stratospheric adjusted radiative forcing, or SARF, efficiencies for ozone. Net SARF is just the composite of the shortwave all-sky and longwave all-sky component with a stratospheric adjustment. And so to apply the kernel essentially for each grid cell at each level, we multiply our perturbation in Dobson units by the radiative kernel, which is in units of milliwatts per meter squared per Dobson units. And we estimate our tropospheric ozone SARF in milliwatts per meter squared. And so the zonal mean image of the ozone radiative kernel here on the left-hand side illustrates that the radiative efficiency of ozone is not the same everywhere, and it's most powerful as a greenhouse gas in the tropical upper troposphere. So here's the results of that kernel application to our ozone perturbation. So now I'm showing the avoided annual tropospheric ozone SARF, which again is just the ensemble mean difference between the world avoided and historical simulations with the kernel applied. The hatching again is where the signal is not robust to internal variability. So we see that the pattern of the SARF is relatively similar to the pattern we saw for the avoided column ozone, but there's a few additional peaks over the North Atlantic Ocean, sort of on the right-hand side of that box, and over the Sahara Desert. Looking at the zonal mean, we see that over 65% of the northern hemispheric zonal mean avoided SARF is attributable to the upper troposphere. So really highlighting this region in the upper troposphere where ozone is important as a powerful greenhouse gas. We average our avoided SARF over these same 3 spatial regions. Sorry, I think I meant to point out that the dots here are the solid dots are the ensemble means, and then the individual light shaded dots are the spread across individual world avoided responses. So for the eastern US North Atlantic region, we see an avoided tropospheric ozone SARF of about 77 milliwatts per meter squared, and then globally averaged of about 15 milliwatts per meter squared. And the range across the individual ensemble members goes from 11 to 24 milliwatts per meter squared. So accounting for that internal variability, our results indicate that US emissions controls may have avoided an additional 3 to 6% of the total pre-industrial to present day tropospheric ozone RF of about 390 milliwatts per meter squared, which comes from that Xi et al. Paper that I pointed out earlier. So this is a small but non-negligible global contribution from regional policy. But of course, we see that the SARF is spatially concentrated. And so if we look at this eastern US North Atlantic Ocean region, looking at the change in SARF since 1970 for this region, we actually find that our US air pollution controls may have avoided an additional 38% of the tropospheric ozone SARF over this time period. We find that there's a strong seasonality in the tropospheric ozone avoided radiative forcing, and that's due to the seasonal cycle in ozone production itself. So here I'm showing the northern hemispheric seasonal cycle of that avoided tropospheric ozone SARF, which peaks in the summertime at about 85 milliwatts per meter squared in July. And then on the right-hand side now, I'm showing the column ozone avoided SARF for the June, July, August average. We see over that eastern US North Atlantic region that we avoid up to about 170 milliwatts per meter squared. So the strong spatial and seasonal concentration of the avoided radiative forcing indicates that US air pollution controls primarily avoided additional ozone RF in the summertime, which might have implications for differences in the climate impacts of this radiative forcing compared to a well-mixed greenhouse gas like CO2 and methane. Okay, and then finally, we can decompose this radiative forcing into its long wave and short wave components, shown here by the pink line and green line respectively. We find that across seasons and across months, the long wave forcing contributes about 70% of the net SARF, which is in agreement with previous studies looking at the pre-industrial to present day contributions from long wave and short wave. The long-wave and short-wave components have relatively different distinct spatial patterns and also different relationships of signal to noise. So I'll just point out here that the long-wave forcing dominates near the source region, while the short-wave is robust to internal variability in the Arctic and contributes actually over 50% of the net SRF here. And this is because you're putting ozone, which is a short-wave absorber, over high underlying albedo. Okay, and with that, I'd just like to pop up my conclusions because I'm running out of time here, and thank everybody for, again, for their contributions to this work. Thank you.
Thank you. Okay, great. The other questions? Yes?
I do. Well, if no one else has one, I'll ask one. I'm not sure this is the only way to depict the world avoided, in the sense that the emissions growth was very rapid between 1950 and 1970, and it probably followed more or less the GDP growth. So instead of just leveling off the emissions, it would have maybe been interesting to let them grow with GDP. And that would have made it certainly much, much worse.
So they do grow with activity driver data, so energy consumption and population over time. It might just be kind of hard to see, but in the US you can see that they are continuing to increase. So you're freezing the emissions factor component, but the way that CESM is calculated is emissions factor times the activity driver. Yeah. But yes, thank you.
You can go to the microphone too, but we'll do one more.
A very nice talk. I'm wondering the radiative forcing you calculate from ozone is like the direct radiative forcing. Have you considered like the ozone changes in like OH level and other greenhouse gases change? Do you have like an estimate how much that would be compared to what you get here?
Yeah, so I haven't calculated that, partly because it's pretty, I think we would need interactive methane emissions in order to fully account for all of the interactions. But actually, it's a good introduction for Xinyuan's work because she finds a sort of, route around that in order to calculate, estimate methane radiative forcing from ozone precursor emission changes. So maybe I'll let that transition to her.
It's a great transition. You may come, but one question quickly. So the same for the aerosols, they would also change, but you haven't looked at that either, I assume.
Yes, that's a really good question. So actually in our first paper in 2025, so we actually do alter aerosol emissions. And so we find a large change in AOD, largely from sulfate. And so we are attempting to use the kernel here to separate out the tropospheric ozone radiative effect. You couldn't do ERF simulations with both the aerosol and ozone perturbations. You'd have to separate those out separately. So that's the benefit of the kernel approach.
Thank you. Okay. Next speaker. Young, you? Go ahead.
Hello everyone, I'm Xinyuan. I'm a grad student at MIT, and today I will share our work about attributing tropospheric ozone changes in the context of internal climate variability and talk about the implications for the transient radiative forcing from ozone and methane. As Steph just mentioned, tropospheric ozone is the third most important anthropogenic greenhouse gas in terms of the potential to present-day radiative forcing, and its radiative efficiency is strongest in the tropical upper troposphere regions. This is the region where we find that in the observations, the observed upper tropospheric ozone trends still increase in these regions, even with the mitigation efforts for controlling the air qualities near the surface. And compare the two plots. On the right shows the upper tropospheric ozone trends, which are basically positive. And this agrees with the model simulations, where we find that after 1995, we can see a decoupling of the tropospheric ozone trends in the upper troposphere in blue versus the lower troposphere in green, in yellow. So this raises two questions: what causes the increase of the tropospheric ozone, and what's the implications for the radiative forcing? To answer these questions is kind of tricky because we need to first of all understand the nonlinear chemistry of ozone formation, and another part is that the changes in ozone precursors also affect methane through changes in OH. So basically speaking, the NOx decrease will lead to the methane increase, but the decrease in CO and non-methane VOCs and methane will lead to the decrease in methane. Combined with the impact on ozone, so it's hard to see what's the impact of NOx reductions very intuitively. And the impact of CO and non-methane VOC and methane is kind of very intuitive with cooling impact. So previous studies use the steady state estimates. They quantify the impact of different emission reductions of different ozone precursors. So basically they find a near zero impact of NOx reductions on the ozone plus methane radiative forcing. But actually depends on different studies. It's basically near zero or even slightly negative. But we live in a transient world, so we want to understand how the transient radiative forcing are from those different ozone precursor changes. So here we want to understand how much of the 1995 to 2013 tropospheric ozone increase is driven by the surface and subtropical emissions. We focus on this source because it's an actionable source. And we want to understand how does that translate into the transient ozone and methane radiative forcing. We run a bunch of simulations, but before I introduce that, I just want to introduce first how the ozone precursors changes over 1995 to 2014, which is our simulated period. And I highlighted the Asian domain where we looked for this study, which is the South plus the East Asia. And we can see that the South plus East Asia emissions, where we show in the dashed line on the bottom, you can see it accounts for most of the increase of the global total surface and subtropical emissions over this period. So we separately look into the impact of that. Basically, we use Wacom 6 to run these simulations, and we run a bunch of initial condition ensembles for 1995 to 2013. And following the protocol of CESM 6, we run 13 individual members for the historical ensemble using the sea surface temperature and the sea ice cover archived from the previous fully coupled simulations in our group. And I picked the 3 members which has distinct ozone trend patterns to generate some sensitivity simulations. Basically, we fixed the forcing agent that we interested in to be at 1995 levels. So for the methane impact, we fixed the lower boundary condition of methane at 1995. For the other ozone precursors, we fixed the surface and subtropical emission sources of them at 1995. We looked at the impact of global versus Asian emissions, and separately we look at the impact of all ozone precursors versus NOx only versus CO plus non-methane VOCs. So in total, we generated 6 ensembles for those sensitivity runs, and each has 3 members. By differencing the historical ensemble mean versus the ensemble mean of one fixed runs, we can identify the signal of the single forcing, and we estimate the noise of internal climate variability use the standard deviation across those 13-member historical runs. And we define the signal to be detectable if the signal-to-noise ratio is larger than the 5% significance threshold, which is a number slightly above 2. Okay, here shows the results. A little bit complicated, but the black dots indicate the 13 individual members, and the ensemble mean are shown as a vertical line. I picked the 3 different symbols as the 3 individual members for the sensitivity rounds, with the red bars shows the 3-member ensemble mean. And the shaded area masks the regions where we cannot see the signal if the signal falls within the shaded area. So we can see that all forcings clearly shows emerged signal of tropospheric ozone increase. And I put here the influence of different ozone precursors, the contributions of them. So it can be seen that the global surface and subtropical emissions of NOx accounts for about 90% of the increase of tropospheric ozone over this period in the historical runs. And importantly, the initial emissions of all ozone precursors account for more than 50% of them. And it's notable that the CO and non-methane VOC emission changes, and also the rising methane that we observed, didn't really introduce the detectable signal in the tropospheric ozone increase over this period. So to deep into it further, I just looked at the 4 different forcings that the signal clearly emerged from the noise, except for the CO2 plus non-methane VOC and also the rising methane one. So I put that here. So here shows the ensemble mean tropic ozone increase spatial patterns over this period, and the heat chain masking regions where the signal to noise is too small, so that the signal is not detectable. And I put the contribution of different ozone practices on the right. So you can see that the impact of the global NOx emissions clearly emerged from the internal climate variability near the Asian surrounding regions. But the Asian emissions are kind of like notable in the Asian and also the Europe regions, but in the tropics, it's basically the emissions from the Southeast Asia instead of the South plus East Asia that we use for this study. Okay, so this kind of research can help us understand where we can find the signal in the observational record. We can easily to seek for the signal of this first thing, for example, in Asia for using the observational record. Okay, this is the impact for the tropic ozone, and then we look into the impact on methane as well. So here I show the changes of methane lifetime quantified by the modeled burden over the modeled total chemical loss. So on the left shows the historical change of methane lifetime over this period, the relative change. You can see that it's basically negative, and it's about 0.6 years methane lifetime shortened. So on the right shows the contribution of different ozone practices. It's notable that the global total emissions, global surface temperature emissions of NOx could account for the magnitude of the decrease of methane lifetime of this period. And the lines shows the NOx emission changes shown as a longitudinal average sum. So you can see that even the Asian emissions account for a lot of the NOx emissions, but they didn't really change a lot of the methane lifetime on the right bottom panel. It's only like in a narrow longitudinal band. And notably that the Southeast Asia emissions actually works a lot on the methane lifetime change. So this kind of imply that we can see a larger impact of the South and East Asian NOx emissions on the ozone than on methane. So we then, first of all, before quantify the relative first thing, we need to quantify the changes in methane concentration. We developed a method to quantify that because we use laboratory conditions, so we cannot directly get that output. So we use the diagnose the methane lifetime change and also the mass balance equation to quantify that. So basically, the observed methane concentration change is about 60 ppb, and the contributions from different ozone precursors are shown here. So basically, if without, so this shows that, for example, the surface emission of global NOx contributed to about 100 ppb decrease of methane, which means if we fix that emission at 1995 levels, the observed change of methane would be 100 ppb higher than what we observed now. But notably, the Asian emissions didn't really impact a lot. So then we quantify the relative forcing using the relative kernel for ozone as DFD, and also use the epicity pressure for methane. So I put the ozone relative forcing here, which is similar to the ozone burden contribution that plot. And then the methane part is shown in blue. So the basic takeaway ideas is that the NOx emissions actually matters more for ozone warming than the methane decrease that led to the cooling. I mean, in terms of the transient case, the ozone warming dominates, which is kind of different from the steady state estimates. And another point is that the Asian emissions, which is the South plus East Asian emissions, really matters. If we reduce the emissions there, we could have larger climate benefits. Okay, so the main takeaways are the simulations accounting for climate variability attribute about 90% of the post-tropic ozone increase to the surface absorbing NOx emissions. And then the net positive relative forcing from the surface absorbing NOx emissions reflects stronger transient contribution from ozone versus methane. And the third part is that the Asian emissions influence ozone strongly, but methane weakly, yielding larger net relative forcing than the global emissions. Okay. Thank you. I will put my acknowledgements here, and I'm looking forward to any questions.
Time for a couple of questions. We can slowly transition to the next talk while people think about it. Thank you. No more questions? Then please go ahead.
Okay, great. So hi everyone, I'm Arlene Fiore and very excited to be here today. And so we just heard from Xinyuan and Steph about these very complex simulations that have chemistry and climate evolving and transient, in a transient sense. And while we're certainly learning from them, it can be very challenging to try to interpret fundamentally which processes are driving what. And so I'm gonna just use the couple minutes that I have to introduce a new tool, a new configuration of CESM that I'm hoping this community will find useful. We're certainly having a lot of fun playing with it. So we have these axes of chemistry complexity and dynamics complexity. And if we look to kind of our climate modeling counterparts, there's been a lot of fundamental understanding that's been built from simplified versions of climate models. And so in particular, people like Brian Medeiros here at NCAR have shown the value of using aquaplanets with their simplified atmospheric dynamics to understand clouds and aerosols, et cetera. And so one of the challenges we have is that at present, in the chemistry space, right, we have the full kind of climate model, and then we have all of the chemistry on top of it. And so what we're trying to add in here is this aquaplanet with chemistry, so that we can take advantage of the simplified atmospheric dynamics, which in this case, we're just prescribing. So it's an atmosphere-only version. We're prescribing sea surface temperatures and just using a zonal mean gradient. I'll show you in the next slide. So we get the Hadley cells, we get jets, but we're also damping the atmospheric noise and the variability a lot, which also means we get the benefit of not having to run as long to look at chemistry-climate interactions. And we also have this perpetual equinox, which means we don't have seasons. So when we set up AquaChem, we're using annual mean emissions as well. And I want to acknowledge Robert Pincus, who is at Lamont, who kind of dragged me into this, and this was kind of a product of many discussions and some funding that Robert was able to get that allowed us to kind of use the hooks that were already in the CESM framework to put this coupled chemistry into the aquaplanet. And Chindan Zhu, who couldn't be here because she's at the Tempo meeting this week, is the person who kind of took this over the finish line and has a paper that just came out maybe a month ago now in James. So details are there. Very, very quickly, this is what the zonal mean SSTs look like in AquaChem on the right versus ChemChem on the left. And then what you see in the bottom is the tropospheric column air mass weighted OH. And so immediately you see that it's the spatial patterns in the emissions, not the sea surface temperatures and the dynamics that are driving at least the first order spatial patterns that we see in the ChemChem full complexity model in OH. The question I'm gonna go through really quickly that you can learn more in the James paper or chat with me at breaks is how does OH respond to a uniform increase in sea surface temperatures by 2K? And Chindan does this both in ChemChem and in AquaChem for one set of simulations just to check whether we trust the response of this simplified model. And here's what the response in OH looks like. And importantly, Chindan also tracked all of the individual pathways for OH production and loss and shows that the relative rankings of how those respond to the 2K warming also are reproduced in the simplified model AquaChem. All right, so just to the punchline, I know we're tight on time here, is just going to very quickly say that the nice thing, of course, now is that we can pick apart the individual processes in this model that we don't have to run for as long and gain some more fundamental understanding. And so what Chindan is showing here is the relative changes in that global air mass weighted OH, actually, well, it's between 60 South and 60 North. We could talk, I'm happy to talk offline about the importance of OH in the tropics, especially for methane lifetime, as we've heard from Ben. But basically then she picks apart what's the response due to just the physical climate change, which is met, versus if you let the soil NOx respond to a 2K warming, and then implement that in this simplified model versus the biogenic VOC. The color shading is just the dark purple, as we think that's the most robust response. We understand very well that as the atmosphere warms, we get more humidity, we increase primary HOX production, and so we have more OH. But the biogenic VOC response moves you in the opposite direction and dampens that physical response, but it's also that temperature response is much more uncertain. And so I'll stop there and move on to the next talk. I'm happy to chat at the break if people want to learn more.
Thanks so much. If there's a quick question, I think that's okay while we transition over to the next speaker. Yeah, Maria?
Nice talk. I was just wondering if you mentioned methane. Is this something that you guys are going to look at next?
So yeah, one of the main motivations for this work is trying to understand what drives the methane lifetime and sort of which processes matter most, especially if we start thinking about perturbing the climate system and emissions at the same time. So yeah, that's something. I just opted here to show OH, but we have methane lifetime in this paper, and also we have work in progress where we're going further with that.
I'll go and look at the papers. And thank you.
Okay, thank you very much. Our next speaker is online. C1 couldn't make it, unfortunately. He was supposed to come. But the title is The Model Behind the Law, CSM ChemChem Uncovers Industrial Impacts on Air Quality. I hope we have him.
Hello, everyone. Can you hear me?
We do, but we don't see your slides right now. There we go.
Can you see my slides?
Yeah.
All right. Should I get started?
See. There we go. We see you and we see your slides. Go ahead. Thank you.
Thank you so much. All right. Thank you so much for the opportunity. My name is Liyuan Wang, and I'm an associate professor at the University of Miami. And unfortunately, I'm not able to attend in person. But today, I'm going to tell a story about how a model essentially shaped a state environmental law. So I'm going to talk about winter air quality, but before I would like to let you know that this is the reason that I'm not able to attend in person, and being in Florida, she doesn't know what winter is, so there's that. All right, a little bit of background. So thanks to the Clean Air Act, the air quality in the United States has been gradually improving, generally speaking, in the past decades. And recently, based on more recent studies, the EPA has lowered the annual PM 2.5 standards to 9 micrograms per cubic meter. As shown on this map here, many of the counties would essentially become out of attainment. So there are two broad issues here starting to emerge. One is wildfires, and the other one is winter air quality. So this figure on the right-hand side here basically shows the monthly climatological surface PM 2.5 in several major metro areas in the past 10-ish years. And you can certainly see that winter PM issue really sticks out. So among these major metro areas, Salt Lake City in Utah, it definitely experienced some of the worst winter air pollutions. So studies in the area has shown that the winter air pollution episodes in Salt Lake Valley are often associated with the so-called persistent cold air pull events, or PCAPs. These unique meteorological conditions essentially causing the pollutants to be trapped near the surface. So a few years ago, we published a paper in ESNT, and the paper was led by my colleagues, Dr. Kara Woman and Noah, and Wyndon Chase, and also played a very important role in the study. So Wyndon was a PhD student back then. So I led the 3D modeling work in the study. So of all the papers I have authored, and I will tell you that this is my all-time favorite, and essentially later I'll tell you why. So long story short, so we found that the emissions from one single industry facility may significantly worsen the PM 2.5 pollution in winter Salt Lake City. Okay, so this is essentially a measurement-centric study. So we used airborne observations collected using the NOAA Twin Otter aircraft and showed very high levels of reactive halogens, the reactive halogen species emitted from U.S. magnesium. So U.S. magnesium is the largest magnesium producer in North America. So to our knowledge, these are the highest levels of these halogens ever measured in the air, except for volcano pools. And these very high industrial halogens cause the considerable ozone depletion in the vicinity of the facility. This is pretty interesting because normally when we talk about ozone depletion, ozone depletion mostly happens in polar regions, for example, the Antarctic ozone hole. And ozone depletion in mid-latitude regions essentially is very, very rare. So these halogens are all very, very toxic. So you may wonder, are they not regulated at all? Well, it's kind of complicated. Chlorine definitely is, because it's definitely listed as a TRI, a toxic release inventory chemical. But the bromine-containing compounds are a little bit complicated. And BR2 was added for reporting. I think BR2 was added for reporting in TRI in 1995. However, BRCL is definitely not included. And U.S. magnesium does not report BR2 or BRCL emissions. But anyway, so the aircraft observations definitely revealed pretty high concentrations in the region. So now we're wondering, how they may affect air quality. So the chemistry can be fairly complicated, but the long story short, high levels of reactive halogens can undergo the catalytic reactions in the atmosphere, essentially rapidly destroy ozone and lead to enhanced oxidative capacity. And there are very rich literature in halogen chemistry world. Basically, the behavior of halogen chemistry and impacts are very well documented. And one very important thing I would like to mention is that the observations combined with a zero-dimensional box model in the study can definitely reveal very interesting local effects. However, the regional effects will require proper 3D chemical transfer model, and for that purpose here we're using the CESM ChemCam, the Musica configuration, which is the atmosphere model with comprehensive chemistry and regional refinement capability. So here I'm listing some high-level summaries of the model. So Musica is essentially a global model with regional refinement capability. In this configuration, the horizontal resolution is about 14 kilometers on the corners. So to evaluate the impacts of industrial halogen emissions on air quality, the observation-derived halogen emissions are included in the model. So okay, firstly, let's take a look at the model meteorology. So we mentioned before that the winter air quality in this region is greatly affected by meteorological conditions. We can see that here during these PCAPS events, the model stability conditions depicted by the potential temperature profiles and moisture profiles is reasonably well captured by the model, and the winds are also pretty reasonable. If you take a closer look at the model of the PM2.5 chemistry here, a significant fraction of PM2.5 is produced from chemical reactions, and we call these secondary PM2.5. And studies have shown that during the pollution episodes, ammonium nitrate is a dominant chemical constituting PM2.5 in the Salt Lake City regions, and ammonium nitrate is produced from NOx and ammonia. So these two are important ingredients. So we can see that from the vertical profile comparisons that the model definitely has sufficient NOx and ammonia, and actually ammonia is even slightly overestimated. However, if you look at the bottom panel here, ammonium nitrate is still underestimated. From this very simplified diagram here, we can see that the OH oxidation is a bottleneck here, and OH radicals are the most important oxidant in the atmosphere. So the underestimation of ammonium nitrate is likely due to the lack of oxidant in the model. So we have a lot more details included in the paper discussing this effect. And if you're interested, also feel free to ping me offline. Okay, so you may wonder, how would halogens affect PM pollution anyway? So we discussed before that halogen chemistry leads to enhanced oxidative capacity, which is demonstrated by the simple diagram here. And we also mentioned that the production of secondary PM in winter Salt Lake City is likely limited by the availability of oxide. Well, basically, isn't that great? The halogens can enhance the production of ammonium nitrate by providing the essentially badly needed OH radicals. It is also important to note that the halogen effects on oxidative capacity is kind of like a secondary effect, which would unfold over time. So this would also result in extended temporal and spatial footprint. So if you look at the regional effect, these three figures basically show the regional impact of industrial halogen emissions. So with the industrial halogen emissions from US magnesium, the model predicts a significant increase in Higgs radicals across the entire region. And as a result, the formation of PM 2.5 is also enhanced by about 20% over the urban areas. And the increase in PM 2.5, you can see that it's largely driven by the increase in ammonium sulfate, which is the dominant component in PM 2.5, and also consistent with previous studies. And now we're going to evaluate PM 2.5 using the EPA Surface Observation Network, which has several locations in the region. And we can see that, that the model, generally speaking, captures the PM 2.5 during the clean conditions and some of the pollution episodes, especially the urban sites in Salt Lake cities, as indicated by the blue circle. The model does underestimate PM 2.5 in some of the locations during some of the pollution episodes, especially over in suburbs, implying that the anthropogenic emissions are better captured in major metro areas compared to the suburban regions. But the key takeaway message here is that if you look at the difference between the red and blue lines, which represent the model simulations with and without the industrial halogens, and we can see that the industrial halogens definitely lead to an increase in PM 2.5 across all the regions, which is particularly pronounced during the pollution episodes. And further winter air quality studies in the area should definitely target unique anthropogenic sources, such as, for example, like residential burning, stuff like that, and as well as the oxidative capacity in winter times. Okay, now comes the interesting part. So the science is by no means perfect, but the message is pretty clear that one single industrial facility can worsen air quality significantly. So the paper has drawn some quite interesting attention, in my opinion, a little bit unusual actually. So the paper was published in February 2023. Within weeks after the publication, the governor of Utah formally requested industrial halogen emissions be included in the Wasatch Front ozone non-attainment area, explicitly citing our work. And later, the Utah State Legislature introduced a House Bill 220 requiring a statewide inventory of industrial halogens and recommendations for enforceable halogen emission standards. So HB 220 was signed in March 2023 and it became effective in May 2023. That was just a few months after the paper was published. And eventually, HB 220 was expanded and signed into law as HB 420 in 2025. And the key provisions included explicit authority for the Utah Division of Air Quality to regulate chlorine and bromine emissions and publish annual public reports. So I mentioned before that this paper is my personal all-time favorite, and it's mainly because this is a very clean example and textbook case of how the atmospheric chemistry fundamental research is directly shaping an state environmental law. Of course, we got pushback from the big magnesium industry. So they actually hired a consulting company and drafted a very harshly worded letter demanding us to retract the paper and threaten us with lawsuit and everything. So in the letter, they even pointed out several issues questioning our study. So I honestly think it would be very interesting if they actually submit that to a journal. I would encourage them to do that. Anyway, this also triggers some very interesting local news and social media buzz. So I'm copy and pasting some of the interesting discussions on Reddit. So for the interest of time, I'm not going to read this, but I'll just leave it here so you can read. My favorite comment here is from this guy. So if you wonder what's the solution to the problem, this dude here gave some very solid advice. Just don't breathe in winter times. It's a joke, obviously, but it also emphasizes something very unique about air pollution, that you can pick what water you drink, what food you're going to eat, but you cannot choose what air you're going to breathe. So all right, I'm going to wrap up with, I would like also, I included this new slide, basically I'm summarizing what we're planning to do in the future. We're definitely not going to stop there. We're going to keep developing a model, more advanced modeling tools, trying to better understand the air quality, especially winter air quality. So based on recent studies, the aqueous process and wet aerosols and cloud and fog droplets contribute significantly to PM 2.5 PM pollution also in winter times. And we have developed a new scheme that explicitly resolves phase transfer and aqueous phase chemistry, offering several unique advantages. For example, if you look at the chemical equilibrium happening in droplets or fog or droplets, that kind of stuff, it might take a while for the system to reach equilibrium. So the way you're implementing those kind of things can actually make a big difference. And this framework was firstly used a couple of years ago, and since then we have fixed a couple of years and made a couple. All right, with that, I would like to acknowledge my colleagues and the funding and the computational resources provided in NCAR. And the one sentence summary is that basically the CESM model, specifically the ChemChem model with regional refinement capability, extends the measurement derived insights across the wider spatial and temporal scales, thus resulting in broader policy relevance. Allow those to take any questions or comments.
Great. Excellent. Thank you so much. That was very interesting. Questions? A question online, yeah. Can you read it?
I don't think it's a question, it's a direct message to me saying we will switch over to you.
No, that's fine. It's from Rafa, and great you're joining us, Rafa, so you can be here. Yeah. No, that's fine. Okay, any other questions in the room? Yeah, so definitely something we need to talk more about is the implementation of the aquarius-based chemistry too. It's impressive what we can do when we do science and influence stakeholders. Yeah. And please, we go to the next speaker, I guess, if there are no further questions. Okay, thank you so much. All right, the next speaker is Yuval with chlorine-mediated methane removal over the North Atlantic, insights from CO isotopic signals and chemistry climate models. Thank you.
So I'm Yu Yang, current postdoc working with Nathan and Peter. So today I'm going to introduce our work about chlorine-mediated methane, so insights from CO isotopes and also chemistry climate models. This slide is not moving. Oh, sorry. So as we know, methane is mainly removed by hydroxyl radicals with contribution more than 90%. And chlorine may contribute to less than 5% globally, but regionally it can be important. So here in the right figure shows in some regions it's from the model. So in some regions, the methane removed by chlorine can contribute to more than 20% in the northern continent and also in the southern ocean regions. Oh, sorry. And in 2023, Van Happen proposed that in order to explain these very depleted isotopes in the autumn seasons at Barbados, we need a very special CO, which is produced between methane and chlorine. This reaction is very special because due to the very strong kinetic isotope effects, the CO will be much depleted in carbon-13, so reach to around minus 110 per mil. So the typical OH reaction with methane will result in carbon isotope is around minus 52. So with this very special CO, they can reproduce these very depleted isotope signals observed at Barbados. And the current chlorine source at those regions is very hard to produce such strong chlorine radicals at their region. And the mechanism is depicted below. So Barbados is around the transport of the stellar dust, and the stellar dust can mix with sea salt particles, and the ion in the mineral dust can catalyze the chlorine from chloride to chlorine radical and then reaction with methane. But this model was based on CESM version 1 and with bulk aerosol treatment. So for this work, we use a model framework based on a more comprehensive system model with solid hydrogen chemistry developed by Fernandez, and the paper is, I think, is already published online. And also we first coupled the soluble ion process with the MIMI, which can check the mineral dust from several modes, and also the combustion and biomass burning ion and also simulate the aging process, which transfer the insoluble ion to soluble ion, and then which can make the reaction happen. And we also evaluate to ion catalyzed chlorine production to evaluate what the strength of the chlorine production rates should be. So here are the details of the two mineral dust sea salt colorization presentation we improved in the model. The first one was came up by Van Hebben and was first applied to Maiden in 2022-24. So the scheme was based on try to parameterize the chlorine production rates based on the soluble ion mixing ratio and the solar intensity. The reaction was limited to surface layer and also in the environment with sea salt mixing ratio larger than 1 ppb. And the other scheme was provided by Chen, which the parameterization was in geoscam and further evaluate in the northern China environment. And the parameterization calculate the chlorine production rates based on the soluble ion molarity and also chloride molarity and also aerosol surface area. It was mentioned both two parameterizations used the chamber studies results to verify the reaction rates. So we incorporate these two parameterizations in the model, and here we show the isotopes whether the model can reproduce the CO isotopes at Barbados. Here the black dots are the observation from Barbados, and the gray line is the default inverse model, and the two colorful lines are for the inverse model results, are the model results from our simulations with we have a Maiden skin and the Chen skin. And we find for the very depleted autumn signals, with including this additional chlorine and the additional chlorine reaction with methane, these very depleted signals in the autumn can be captured by the model. But this inverse model is only for Barbados, and also because we have some observations from Tenerife is the red triangles. So we first evaluate whether the model can capture the shifts of the isotope between Tenerife and Barbados. So here in the bottom plot, we show the model simulated shift between the size and also from the default Van Heppen's model in CESM version 1. And we find with our model, we can better capture the shifts between the two sides. However, the current models, they have one simplified treatment. So we are only tagging the CO from the methane reaction with chlorine and calculate the shift in the isotopes based on a background of assuming around 25 per mil. So we use a fixed isotope shift from the methane oxidation with chlorine of 110 per mil. A new way is to use a full isotope of different isotope signatures of different CO sources. So similar to methane, which have different source signatures of the source and the sink, carbon monoxide is also the same story. So for example, the CO from biomass burning is much enriched in carbon-13, so it's around minus 18.5 per mil. And for the CO from methane station, it's much more depleted in carbon-13. So here we include all these 6 tags from 3 sources and to check whether we can reproduce these very depleted isotope signals at Barbados. We also have some new observations thanks to Chloe and Thomas, where they collect the CO and the CO isotopes at Barbados and also Cape Verde and Tenerife. They have more data, but here I only show these 3 sites at North Atlantic. So here different color in the plot is for different year, and the black line shows the 3-year monthly mean. So here the left column shows the CO isotopes from the 3 sites. We can see they have a very clear seasonal cycle with much more enriched in the winter and summer, with more depleted in the summer. Between the sites, we also notice for Barbados is additional 3 to 5 per mil more depleted in the summer. In the right column, we show the CO at the 3 sites. We can also see a seasonal cycle, but it's not that strong as the CO isotopes. We can find the CO is higher in the autumn and winter, but less in the spring and the summer. So we first analyze whether the model can reproduce these CO and also CO isotopes. Here the left bar plot shows the seasonal changes of the different CO sources. Here we can find methane station, as noted by the green bars, is dominant the CO source over the three sides. And another contribution is anthropogenic for the CO. And in the summer seasons, methane station can contribute to more than 60% of the CO. And here the right panel plot shows the model simulated CO and also model simulated CO isotopes. The black line is for the model results and different colors for the different observation results at the three sites. So here we can find the model can capture the CO and also CO isotope, the seasonal cycle very well, but the CO is systematically underestimated. So the observation is around 100 ppb, and for the simulations it's around 70. So it's around 70 ppb underestimated. And for the CO isotopes, we can find it's also the simulated CO isotope is more than 10% per year depleted in the model. So in order to match both signs, CO concentration and also isotopes, we build a simple inverse model, try to match to inform us what the source we need to scale up and what the sources we need to scale down. So you build a further model based on the CO concentration and also normalize the isotopes because they are in different units. So we need to think of a way try to make them at the same weighting for the inverse model. So due to time limitation, I will not discuss the details for the inverse, and feel free to chat with this about my setup of the inverse. Here I will show the results for the inverse we have now. So we did 3 inverse tests. One is only considering the CO concentration because the model currently underestimate around 30% of ppb. So here the black line shows the observation and the gray line shows the prior model simulated results, and the black line shows the colorful line shows the posterior. And we find in the test 1, if only to consider the CO, the inverse will suggest we are to scale up all the sources. But with scaling all the sources, it will make the isotopes worse. So it's not matching the isotope signals. And in the inverse test 2, where we only need to match the CO isotopes. So as a reminder, the biomass burning source is much enriched and the methane station source is much depleted. So because the current model simulated much more depleted signal, and then if only consider the isotopes, the model suggests us to increase a lot for biomass burning because they are enriched in the isotope, and scale down the methane station, so it's around 0.5%. So, and in the inverse test 3, which we need to match both signals, and we find the model is struggling to match both signals. We can improve, but we cannot make the posterior very close to the observations. So we are still optimizing the inverse framework, like using different covariance to better address this issue. We also checking, so currently we are using CMIP 6 emission inventory, and we also compare what the CMIP 7 brings the changes. Here the blue line is for CMIP 6 emission, and CMIP 7 emission is the orange line. We can find CMIP 7 suggests much lower CO, anthropogenic CO emission. And for biomass burning, we can see CMIP 7 is more realistic. After 2015, this is the year where the CMIP 6 has an emission. And for the spatial difference, we can find in CMIP 7, there is much less anthropogenic emission over the polluted regions. And for biomass burning, there are more biomass burning source over the Canada and Australia, and also some parts of the South Africa. We further check whether there's some chemistry related with the CO. So here we compare with the results of freeze in 2022, where they coupled the GSCAN in CSM. So as the top left panel shows, the GSCAN in CSM can simulate less bias over the North Hemisphere. In the right column, actually we also find in the current model setup, we can reproduce similar results where the CSM with GSCAN also simulated less Northern Hemisphere CO. But when we compare with the surface observation CO as the several in the middle plot shows, here the red dots are for the CSM coupled with CAN-CAN, and the blue dots are the CSM with GSCAN. We find even the GSCAN has smaller bias, but the correlation is also very small. It's only R square is only 0.28. And also the regional difference is also much larger in the GeoScan, in the CSM with GeoScan chemistry. So the CSM GeoScan model reduced the global mean bias at the cost of the worst spatial correlation and also larger tropical overestimates. So with that, I want to summarize that Barbados, from the observation, we can see there are some episodic depleted CO signals and also with depletion around 3 to 5 per meal relative to the other North Atlantic sites. And the current CSM model underestimates CO and also is over-depleted in carbon-13. And our current inverse model suggests that there is lower biomass burning and non-mesothelial oxidation source. And we summarize that the current model bias makes it challenging to isolate the signal of methane oxidation by chlorine radicals. So for the ongoing work, we are still trying to optimize the inverse model and try to build a model framework where we can quantify the change, the methane contribution from chlorine radicals. And also we are working on to understand this process at the process level, where we are going to couple a particle resource model with mosaic and also archaeochemistry to better understand these reaction rates and compare with some lab results. So with that, I'm happy to answer any questions.
Thank you very much. Questions? To the part 2, you're talking about a particle-resolved aerosol model. What do you mean by that?
Particle is a PaLM-C, so developed by Professor Nicolino. So we are trying to check the particles without side spin or model-model approach. So it's per particle where we can check the particles individually.
Is that coupled also to the CSM version?
No, so we want to first to understand the rates, and then maybe at different size range, maybe the rates are different, and then we will use this information to inform the current parameterization we have. So maybe we will not cover this model in the CSM, just use these reaction rates, because currently it's very simple. It's just based on some soluble ion ratio. There's no parameterization based on acidity or maybe the size range of the other aerosol species. Yes.
All right. Any other questions for our speaker? Then thank you again for the talk. And our next speaker is Xiaohong Liu. I hope you are online with radiative effects of biomass burning aerosols on the Arctic using CSM2.
Can you hear me?
Yes, we hear you. Great. And we see your slides.
Thank you for the opportunity. Yeah. I'm sorry I couldn't join the meeting in person. So I'm going to talk about the radiative effect of the Boreal biomass burning aerosol on the Arctic using the CSM tool. So this work is the most done by my postdoc Wei Yi Wang, and also is a collaboration between TechCEM and also the anchor like Wen-Fu Tang and also Louis Emmons. We know that the Boreal Wi-Fi has been increasing in the past decades. So this is a figure showing the GFED by black carbon emissions trend over the past 20 years, and you can see clearly that in the Boreal regions in the Canada and also in the Siberia, that the black carbon emission has been increasing in the past 20 years. So then these, we know that the Wi-Fi can emit trace gases and aerosols and also water vapor into the atmosphere. Then also one of the, in addition to the emission flux, emission amount, the injection height of the Wi-Fi's can influence the transport and lifetime of the gases and the aerosols. And then this Boreal Wi-Fi emitted aerosol, they can transport to the Arctic. This study showing that this Wi-Fi aerosol can reduce the sea ice loss when they are transported to the Arctic. And then, however, the only few models can interactively simulating calculating the vertical profiles of Wi-Fi aerosol emissions, like in the CESM2 model, they injected the Wi-Fi aerosol emission and gas emission only at the surface layers. So this study, objectively study, we incorporate a plume-rise model in the CESM2 and also investigate the radiative effect of the Boreal Wi-Fi's on the Arctic. You see. Okay. So the method we use is the Musica version 0. This is the configuration of the cam in the CESM2, and you can see over the continental US, there's a high resolution that's about 14 kilometers, but over the outside these focused region, the continental US, the model resolution gradually decrease and to like 100 kilometer resolution. So we're using Musica version 1 to start look at these biomass burning aerosols. And so in addition to that, we also implement the plume-rise model based on the FRITAS into the CESM2. So basically, the plume-rise model used the MODIS observed fire radiative power and the heat flux, and to calculate the injection height solve some equations for the temperature and the updraft velocity and the hydrogen media, and to calculate the injection height of the emissions of biomass burning aerosol and gases. And so the biomass burning emissions are based on the FIN, and this is developed by Anchor, and to include the species like black carbon and particulate organic matter, POM, and also the trace gases like CO, SO2, NOx, and VOCs. In order to validate the model with the observations, like we run the simulation for a period August 2018, and this is during the weekend field campaign. Like you can see in the Western U.S., there's a field campaign the weekend taking part into the in the Western U.S. These red dots is showing the emission based on the particular organic matter emission based on the FIN emission. Yeah, data set. And so this is showing the August 2018 the particular organic matter emissions. So we look at the Arctic region and the Boreal region. So we conduct the 4 experiment in this in our studies. One experiment is without Boreal Wi-Fi aerosol and gas emission. So basically, we have on and off of the biomass burning emission in the Boreal regions. Boreal region we define as the 55 to 70 degree north. And in addition, we have a tool experiment. We look at either turn on the plume-rise model or without the plume-rise model. Basically, if without, we emitted the biomass burning emissions at the surface, the same as at the CESM2. And this is showing the CO and this column density with satellite observations for the August 2018. This is from satellite. This is 2 models. Like the one is the based on Musica, and this is the middle is the plume-rise, and the right is we emitted biomass burning emission at the surface. And basically, you can see the 2 model configuration can simulate the CO column burden compared with the satellite observations. These like the patterns and also magnitude reasonably well. And we look at compare these aerosol and gas trace gas vertical profile with the weekend observation listed like in the North America, and you can see the vertical profile of the left is the black carbon, the middle is the organic aerosol, and the right is CO. And the black curve is from weekend aircraft observations, and the blue and the red is from the surface. The two model simulations. One is the immediate at surface, another is we immediate by spooning based on one plume-rise models, and the red. And you can see the two model simulation basically can simulate capture this vertical distribution of this aerosol and the CO, and the two model versions generally the difference is not as big. But if you look at the altitude above the 2 kilometer, you can see that the plume rise model red can increase the aerosol BC and organic aerosol and also above 2 kilometers. And this is this is the impact. The change is less than we expected, but maybe because because of model vertical resolutions. Even we increase the horizontal resolution, but over the 2 kilometer, the model is cost resolution of 1 kilometer. Maybe it's not the impact of the plume rise is not as we expect. But for the CO, you can see the impact can be large and on the vertical profile. And then we look at the Arctic transport to Arctic, and this is showing the zonal mean distribution of the primary particular organic matters, and between the two simulations, with and without the biomass boreal regions. And this is the left is with plume rise, and the left is plume rise. The right is we emitted at the surface. So you can see that the boreal Wi-Fi's can increase the POM, like particular organic matter, this is plume rise POM have from the boreal region can transport towards Arctic. You can see transport to Arctic, and if you compare the two simulation, one is the plume rise, one is immediate at surface. You can see the plume rise have more aerosol transport vertically, and also more transport to Arctic. So next, we look at the impact on Arctic and this related effect of aerosols. If you look at the primary organic matter burden change in Arctic, and the 7-degree north, and this is the left is the plume rise, the right is the immediate surface. The middle is the immediate surface, right is the difference between plume rise and the surface. And you can see the Wi-Fi, boreal Wi-Fi increase the POM and by like 170%, and while if you immediate surface increase only by 130%. And so they basically you have more aerosol transport to the Arctic if you have plume rise. And this is showing the AOD, aerosol oblique depth change, and so you can see the boreal Wi-Fi can increase the AOD like up to 0.4. This is pretty large values to the Arctic, and this more transport to the Arctic if you have turn on the plume rise compared with if you immediate at surface. And this is showing the AOD that look at the related effect due to the Wi-Fi aerosol radiation interactions, and the left is if you turn on the plume rise, and the effect can be 6 watt per square meter across the Arctic. And so basically, if you compare with the immediate surface, you have more stronger radiative effect, more cooling, and the cooling difference can be a few watts. Like if you look at the right, and there can be 2 to 6 watt difference. And so this is if you look at the aerosol cloud interaction, the ACI, the radiative effect, and generally this cooling effect due to the ACI and in the Arctic because of the boreal Wi-Fi's. So, and then, however, if you look at the Greenland, this the warming effect, and see the cooling effect can be reached 8 watt per square meters, and this is this increase of this stronger radiative effect due to ACI is because of the increase of cloud droplet number concentrations due to the barrier Wi-Fi. So you can see this is the increase of the color droplet number concentration due to the barrier Wi-Fi can be 80%, and if you only immediate at surface, it's like the 70%, and also it increase of the cloud liquid water pass, and this is the increase. And so we also look at the snow darkening effect. So basically, the biomass burning aerosol like black carbon they deposit on the snow and ice. This is showing the warming effect in the Greenland. So this is a few up to the 1 or 2 watt per square meter, and this is and this certainly if you have plume rise, the transport high, they can have more transport to the Arctic. They have stronger snow darkening effect compared with if you emit it at surface. So if you look at total effect of like surface net relief flux change and due to the Wi-Fi, body Wi-Fi's, and so this is the difference can be 10. That's the net flux change reduction can be like 10 watts per meter, and this is certainly it can influence the warming over the Greenland can be also a few watts per meter. This is a pretty large number. It can impact on the sea ice and also this Arctic regional climate. So this is showing the summary, and the plume rise model is we implement that in the CESM, and so we can interactively calculate simulate the vertical injection of biomass burning aerosol and gases, and then we see that with plume rise model they can they inject more aerosol into the above 2 kilometers and gases, and then they enable the more transport of the aerosol gas into the Arctic, can increase the aerosol and also the droplet number concentration, and the cooling effect of the aerosol can be the net cooling effect on the surface can be like by 32%, like from the 3.4 watts per meter to up to the 4.5 watts per meter the cooling in the Arctic. And this is all. Thank you very much.
Thank you very much. Are there questions? I just have a quick question regarding the radiative forcing. Is that over a certain time period you calculated it?
Yeah, so this is for August. So for August 2018.
Oh, just August. Yeah, thank you. And just that 1 year?
Yeah, it's just 1 month,
Yeah.
actually August in the summer. And so we also simulate for longer simulation, but due to limited time, we all see for 20 years, the period of from 2000 up to the 2023, so the long period of time. Yeah, but because this is just showing the comparison with the observation, which only show the August 2018. Yeah.
Okay, and
Hello, thank you for your talk. This is Pieter Nel from NCAR. Did you have a means to basically validate your plume rise, so how high the aerosols were in August 2018?
Yeah, so we compare with the weekend, and also, this is the weekend, this is the aircraft observations. This is the vertical profile. Yeah, we also compare with other field campaigns like the 5AQ observation. Yeah, 5AQ for that campaign, the difference is bigger. For if we emit at the surface or emit at the high altitude. But we certainly we can. This is we certainly need more observation to validate the plume rise model. Yeah. We see that they certainly have a big effect on transport to the Arctic and to the.
Thank you.
Okay, thank you again. And we'll transition to our next speaker, which is last name Ali Akeradi. Okay, and he talks about aerosol microphysics, model intercomparison, and machine learning emulation for stratospheric aerosol injections.
at noon before lunch. Okay, so yeah, I'm going to talk about aerosol model intercomparison and machine learning emulator. I'm not going to spend time talking about emulator, given the, for the time being. This is this slide. Okay, cool. So punchline. If you use different models for aerosol scheme within GCM, you're going to get different results. So this is from Simone's paper, recently published. If you use MAM versus Karma or other models, perhaps you're going to see almost by factor of 2 differences in terms of sulfuric burden. This talk is just going to focus on this sulfuric acid and SO2 purely. So that's like, to make things simple, basically. If you look at other studies like Ilaria's from NCAR at 2023, you can see if you run different models and compare to measurements, you see a different suit of comparison. The results are different, basically. And if you look at Pierce et al. At CSU that published in 2010, look at the effective radius of the aerosol and look at the cooling effect. It's very sensitive to size of the particles. So for an example, if you compare 200 nanometer particles versus 600 nanometer particles, you get 60% of the cooling. Consequently, if you look at the gravitational settling, the lifetime of the particles are going to be vastly different. So in this case, I just assume 20 kilometers up in the atmosphere for 200 nanometer particles and 600, and you see by factor of 3 differences in terms of lifetime. So it's very sensitive to what your effective radiuses are. So this is the motivation of doing the model comparison and see why the models are different. For this study, I spent time porting 3 different models from Fortran into Python JAX that Duncan Watson-Paris talked about earlier yesterday. This is a differentiable model. I picked MAM, which is a model from NCAR. Karma also is a sectional model from NCAR. Thomas is the model I worked during my PhD, and it's coming from Caltech, developed by John Seinfeld and Peter Adams. And I ported these over past few months, and now it gives the framework of being able to tease out different processes. So you can look at the coagulation, you can tease out condensation or nucleation, and run diagnostics to see how much of a difference you get from different models. For this study also, I picked part MC. It's in Fortran still. And this is a particle resolve developed at Urbana-Champaign by Nicole Riemer and Andrew West as like a reference for the comparison. So I'm going to spend time talking about 2 different processes, coagulation and condensation. First one, coagulation. This is just one example for the sake of the comparison, given that MAM is a modal model. I don't have flexibility in terms of the width of the distribution, so I have to specify sigma the way that MAM represents. So Aitken mode, it's 1.8. For this example, I initialized the mean diameter of 20 nanometer. This is basically the same plot. The y-axis is showing the number concentration. The right side is the linear scale, the left side is a log scale. So if you run 6 hours forward, you can see that, can I use this one? Oh, yeah. So there are these gray lines are the part MC100 simulation, and the black one is the average of the simulations. Red is Thomas, blue is MAM, and green is Karma. So Karma seems like it has faster coagulation, and they reduce the number concentration faster than the other models. If I do 5 more simulations, different mode, 2 Aitken, 2 accumulation, 1 bimodal, the story holds. Karma is just having the faster coagulation rate. If you look at the volume distribution, same story. And this is much easier to look at because it's the normalized and total number concentration. So the green, you can see that it's Karma, and it's just, and the coagulation rate is faster. So the question is what coagulation depends on. There are 5 different factors that you can calculate the kernel for the coagulation. There's air viscosity, air mean free path, slip correction factor, particle diffusivity, and thermal speed of the particles. So if you look at models, and just, I don't want you to just spend time looking at it. It's just, the point is each model calculate these differently. I got some comments from my group that I shouldn't have the dashed line. The reason I have the dashed line is because MAM for the slip correction factor only used a single value to transition. So that's why there's dashed lines and it's not consistent. But overall picture, these values are not consistent between the models. That's why you get different results. Now condensation. So for condensation, I just ran 3 different simulations, and this is ongoing work. Again, initialize the size distribution with the sigma of 1.8 in Aitken mode and 20 nanometer mean diameter. And then I introduced 3 different constant H2SO4 concentration in the gas phase. The first one is 10 to the 7 molecules per centimeter cube, 10 to the 8th molecules per centimeter cube, and then 10 to the 9th. The bottom one shows the total condensation of the H2SO4 after 6 hours. So I run the model forward, just look at the differences. So blue again, MAM, red is Tomas, and green is Karma. So, sorry. So then you can see that the condensation rate in MAM is slower than Tomas and Karma, and Tomas and Karma still disagree, but they are not very close. So again, the question is what condensation depends on. So the condensation, besides diffusivity and Fuchs correction factor and water uptake, also there's 2 other factors, which is vapor pressure and also Kelvin effect. For sulfuric acid, those don't matter because it's a low volatile species. It has a low vapor pressure, so that doesn't matter. That's why I didn't include those. But if you look at the diffusivity between Karma and Tomas and MAM, you can see the differences. And the biggest one is water uptake. Because condensation depends on the wet diameter, not the dry diameter, it's really important how much water uptake you get for individual particles. So I looked at the models. These are the models I basically cloned from the GitHub repositories and was in the default mode. So for Tomas, I saw that the water uptake depends on the ammonium bisulfate, not pure sulfuric acid. Karma has a pure sulfuric acid water uptake, which is based on Tabazadeh 1995 paper. And MAM uses the Kohler parameterization, which doesn't really represent the sulfuric acid. So out of curiosity, again, included Tabazadeh's parameterization in Tomas, and you can see there is a slight differences, but it's still, it's getting closer in terms of water uptake. And then I ran the simulations again. Now you can see the updated parameterization in Tomas agree much better with Karma, and the solid red line with the green agrees much better. So you still see differences in terms of the total amount of H2SO4 condenses, and again, it goes to the diffusivity calculations and all the other underlying code that it's different, but you get better agreements. So why does this comparison matter? Going back to the effective radius of aerosols. So just looking at the single simulations that I showed you, the Aitken one, if you run the model with the coagulation and condensation and normalize the size distribution, these are the size distribution here. And then if you calculate the effective radius, you can see that, these are the points. So the bar chart showing basically those values. So you can see this is relative to the optimum diameter, which is 223 nanometers, I believe. And you get almost by 30% differences between the models. So that's really important in terms of radiative forcing effect and the sulfuric acid burden. in the atmosphere. I want to emphasize that there hasn't been any work in terms of unifying model intercomparison for aerosol box modeling, and it's very important to have one in order, because there's so many different models from different groups, and everybody does different work and different field campaigns, different measurement, different chamber experiments, etc. So there has been an effort done by PNNL group led by Lara Fierce that they call it Amber Projects. They try to have a framework where you can plug in your aerosol box model, then run it with the same initial inputs, get you a net CDF file from all the models, and then it makes it easier to compare with each other, which is pretty exciting, and hopefully it gets traction. So for the future work, obviously I didn't include, I have to think about more species, not only sulfuric acid, also add more models in terms of the comparing the models together, because there are a lot out there. The other one is exploring nucleation schemes and how nucleation will differ between different models, adding part MC as a reference for condensation. One thing with the sectional models that, converting mass from one bins to another, it's tricky, and there's like solvers, etc. Part MC represent individual particles, so it makes it easier to do different processes. And then running ensembles, try to understand what's the average and medium spread between the models are. And we are working on building and improving AI emulator that we have had some exciting and very good results so far. Oh, by the way, these are all the repositories. If I also created an app for Tomas that you can go, if you scan the QR code, it's not going to show on your cell phone because you need a laptop or tablet, but you can see the URL, and you can use the URL. You can run the model on the cloud and see all the results and graphics, so you don't need to set up the model. Just want to acknowledge the team at Reflective. We are working on a multi-scale modeling project that we are trying to build emulators for different scales, from GCM to get the transport into the emulator, all the way to plume modeling, to large eddy simulations and aerosol microphysics, with the hope that we can run these models faster, and then eventually explore the uncertainty much easier. You can run ensemble many times. This work is also funded by Estera Foundation, which we are grateful for. With that, thank you so much for your time. Appreciate it.
Questions?
Yes.
Thank you for a really beautiful talk and some really amazing work.
Thanks.
Truly. Have you thought about putting organics into this model?
Yeah, I did my PhD in secondary organic aerosol. It's, as you know, representing different species is tricky, but I'm working on bringing VBS, volatility basis set, and also a statistical oxidation model into JAX as well, so it makes it easier in terms of plug-in, and then you can explore, these questions, how you're gonna do, And then the beauty of that is it's not gonna be only in Tomas, which I worked on, then you can easily plug it into MAM or, into Karma or any other models, and you can explore organics.
Karma model does include a mixed aerosol as well. I don't know, that does include the VB, but yeah, it just can include this. You have to prescribe.
For sure.
I had a quick question, if there's no other question. Go ahead.
Thanks, Ali. You didn't mention it, but how faster was ultimately MAM and Karma, for instance, compared to the Fortran version?
Good question. On CPU, you get similar results with Fortran, maybe by factor of 2 slower. The whole point of having everything on JAX, as Duncan mentioned yesterday, is, on GPU, you can scale everything. It's the game of scale at the end of the day. you can run on a single GPU 10,000, 100,000 simulation much faster. So the test I have done with Cheerios, that you can run 100,000 simulation in less than 40 minutes, which is pretty good for more than 24-hour simulation. So it makes it much easier. Also, the jacks give you differentials, so you can just run the differentials much easier. You want to say how sensitive my coagulation kernel is based on the range of the temperature. You don't need to set ensemble. You can just run single simulation and get the output.
Right. Yeah, just a quick question on the diversity scheme. That is also in MAME. So I wonder why MAME and Karma look so different. But we can also discuss that offline.
Yeah, I would love to.
Yeah, it sounds like a longer discussion potentially,
yeah.
since it's the same condensation scheme, but it's very different.
Yeah, I was surprised also, but I was surprised how calculation of the air density is different. It's like basically should be the same. It's like this kind of stuff. It's textbook equation. It should be the same.
Yeah. We had some kind of thoughts on that earlier too. Great, and there's more things we can discuss. But yeah, I thank you very much.
Yeah. Thank you.
Yeah. So I think we learned that the last speaker is not here. He was online, remote, so that means we can thank all the speakers again and all the contribution. And if people want, we could have a quick discussion, but people may be also eager to go for lunch. And I think I see people nodding. All right. We'll do our discussions in the winter meeting. These are the meetings we show the science, as Peter Lauritsen also said last time in the atmospheric session. In the winter meetings, we'll have the co-development discussion, and I hope I see you and most of you again in winter. Thank you so much.